Hello, good morning, everyone. Can you hear me? My name is Edilberto Sanchez, and I am the chair of the workshop program committee. And it is a great pleasure for me to give you a very warm welcome to this fifth edition of this Fusion High Performance Computing Workshop. I will host this welcome session on behalf of the entire program committee. And let me present the rest of the program committee that is here. I want to thank them for the great job preparing an exciting and interesting program for this event. And we also want to thank all the institutions that collaborate in the organization of this event that appear on the right. And of course, we want to thank the local organizing committee that makes everything go smooth in this event. Thank you very much. The event was initially promoted by the Spanish Supercomputing Network. The first edition was celebrated in 2020, and it was celebrated online. And this online event allowed for the participation of many people from different countries around the world. And the interest of the high performance computing for fusion was readily recognized, and the interest in the event has increased during these years. As you can see in this plot on the left, the number of registration for the event has increased a lot since the first edition, and also the number of countries where the participants come from. Let me give you a glance of the program of this event. Over the 2 years of the event, we will have 3 kinds of talks. First, we have keynote talks that are 45 minutes, including 10 minutes for questions. We have invited talks that are 30 minutes, including 5 minutes for questions. And then we have contributed talks that are 20 minutes, including questions. You have here the program for the first day, and you can see that the talks are grouped into sessions with a common thematic. And between sessions, we have some breaks. Today, we have 3 breaks. We have a break at 10:45 in the morning, a 20-minute break, and then we have a lunch break at 12:05 of 1.5 hours, more or less. And then in the afternoon, we will have another break of half an hour. We have parallel sessions, you can see here, and all the keynotes and all the invited talks are in plenary sessions, while the contributed talks are all in parallel sessions. Due to a last-minute health problem of the speaker, the first talk in the second session this morning is canceled. We hope that the speaker, Andrea Sand, recovers soon. This is the program for the second day. We have a similar structure with 3 breaks also, and in this case we will have tomorrow 2 parallel sessions, one in the morning and one in the afternoon. And when we have a parallel session, we will have 2 rooms, 2 Zoom rooms, and you will have to switch between rooms. The rooms are called main room and room 2, and the switch is very easy. When soon before the parallel session start, a button will appear in the bottom panel of the Zoom window that is called breakout rooms. This way you can choose the room to which you want to go. You have to press the button join a break room and select the room you want to go. You can choose go back to the main room if you want. And whenever you want during the session, you can go back to the main room. In any case, when the parallel session is over, you will be redirected to the main room automatically. You don't need to do anything, okay? As in previous editions, we will have an expert review of the early career talks, and this early career presentation will be assessed by two experts, and a feedback will be provided to the presenters based on a rubric. The rubric is this way. I'm showing here on the right an example of the kind of things that are assessed in the rubric. And the goal of this process is providing support for the professional development of the early career scientist by giving the feedback. If you have any question about this process, you can send an email to hpcfusion@bsc.es. Also, as in previous editions, we will have a selection of the best presentations by early careers scientists, and we will select the three best presentations as outstanding presentation, and they will win prizes and a certificate. The winners will be announced after the workshop in the website, and the prizes for the winners will be the novel by Dan Brown, Origin, and a pair of earbuds that are sponsored by the Laboratorio Nacional de Fusión at CIEMAT and the Barcelona Supercomputing Center. Maybe you wonder why this novel. This is because this is the action of the novel is located in Barcelona and features the Barcelona Supercomputing Center and the Mare Nostrum. This is why this novel is given in this event. We will also vote for the favorite talk. We will select the most popular talk, and the favorite talk will be selected among the invited and the contributed talks, and everyone attending the meeting will be able to vote. The voting will be carried out after the workshop in this occasion, and the participants will receive a link for it after the event. The winner will also be announced after the workshop in the webpage of the event, and the presenter of the selected as favorite talk will receive a certificate also. I want to remind you some practicalities. Point, we will have two virtual rooms only in the parallel sessions with connection details that are sent by email to connect directly to the session. Please keep your camera and microphone off during the presentations. And you may ask questions using the raise hand function in the Zoom window, or you can use the chat and write your question, and the session chairs will voice the questions from the chat and select the people with raised hands to unmute and allow them to ask the question. All the workshop will be recorded and will be shared online afterwards. And if you have any questions or comments, you can send an email at any time at hpcfusion@bsc.es. You can try to use this functionality now and try to send messages to other colleagues. You have the function to send messages to everybody or to a particular person. But please be sure that the camera and the microphone is off when the first session starts. Then we came to the end of this welcome session, and I only want to thank you for joining. And now we will have the opening session that will be chaired by my colleague Yasuhiro Suzuki. And I don't know if Yasuhiro is ready to take over.
Yeah.
Okay,
So shall
so
we keep the
the floor is
schedule?
yours.
Shall we start now? Okay. Okay, so thank you very much, Eddie. So my name is Yasuhiro Suzuki, so Hiroshima University from Japan. So as Eddie mentioned, so this the first session consists of the two plenary talks, and the time is the total the 45 minutes, including the 35 presentation and the 10 minutes the discussions. So about the discussion, so please use a function of the raise hand, or if that function doesn't work, please put your question in chat window. I will read your question in the Q&A sessions. Okay. Okay, so Jae-Min, are you ready?
Yeah, I'm connected. Can you hear my voice?
Yes.
Okay, so let me start sharing my screen.
Yeah.
Okay, so
then I am very happy for chairing this session. So first keynote speaker is Jae-Min Kwon from the South Korea. Title is Digital Twin Technology to Accelerate the Fusion R&D. So please go ahead, Jae-Min.
Thank you very much, Chairperson. My name is Jae-Min Kwon from Korea Institute of Fusion Energy. Before I start this presentation, I'd like to thank organizing committee for giving me this great opportunity. It is truly my pleasure and honor. The title of my presentation is Digital Twin Technology to Accelerate Fusion R&D. And I'm presenting this result on behalf of our virtual K-STAR development team. It is truly a multi-institutional development team, closely knitting all these institutions listed on this right-hand side. So this is the rough outline of my presentation. First, I'd like to introduce what digital twin technology I mean, and then I will discuss a list of enabling technologies for this fusion digital twin. And then I will present our recent development of virtual so-called K-STAR based upon this fusion digital twin technologies. And then we'll present and discuss some ongoing and future works. So first on this digital twin technology, this digital twin technology, this keyword is used in somewhat broad manner in different discipline of scientific and engineering researches. But generally, it can be defined it as a collection of IT technology to virtualize shape and functions of complex object and in different degrees of sophistication. Probably the most primitive one would be something like this level one, virtualization of the shape of real object with some minimal its properties and data. And a bit more sophisticated one would be the connection with real world taking measured data from that real-world object. And probably the highest sophistication level would be the virtualization of certain object with integration of simulation and analysis capabilities based on, for example, AI or machine learning in this day. And there are many actually examples of this relatively lower level digital twin. For example, this level 1 or 2 examples like digital asset management based on this kind of the commercialized digital twin software, or design and construction management based on this digital twin technology, or a little bit more specific example here, but I'd like to bring some recent development in this nuclear fission industry, try to digitalize the interaction of this operator and the machine in this highly sophisticated way. And regarding this application of digital twin in this fission or nuclear fission, the industry, would be interesting to compare this different discipline or technological area. However, but with many sharing features in especially near future as a neighboring technology, namely the fission and nuclear fusion. So for fission, we already well know we have commercially operating plant with huge available data from this operating machine, and of course well-validated simulation for its operation and design. So usually the digital twin development aim to improve the safety and efficiency of those existing plant. On the other hand, fusion, we are still in research and development phase, and also limited data from existing device and simulation technology. So purpose of our event, for example, still on the active and heavy development. So it seems digital twin technology for fusion usually aim to accelerate this research and development phase by advancing this digital twin level up to this 3. And whether we used this keyword digital twin explicitly or not, this concept has been around us over past 10 years. For example, this kind of remote maintenance study conducted in JET Tokamak, they certainly utilize this digital twin concept, and also the virtualization of this kind of the complex 3D geometry and the simulation result in a large helical device in Japan, or design and construction management of a fusion device like ITER, that's very actively undergoing in this day. Certainly they share this kind of technology, certainly share the concept of digital twin. And recently, this digital twin is rapidly evolving, largely thanks to this the improvement in this CPU and GPU supercomputing. And I just here listed most recent result, but certainly I believe there are many more. For example, this left-hand figure shows digital twin technology development, which is being conducted in general atomics, centered around this 3D Tokamak virtualization, with this concept of so-called super facility, or the fast machine learning surrogate for fast simulation. And the last example I'd like to refer is this recent effort on UK for the design of next generation fusion reactor based on this digital twin technology. And along with this, the worldwide effort, we also recently started this development of digital technology to target this virtualization of the existing tokamak we have, the K-star, so development of virtual K-star. So this movie shows basically our concept. We'd like to virtualize existing K-star device in this digital space with short-term goal to facilitate the day-to-day machine operation and experimental analysis, and a bit longer-term goal the support of simulation analysis for machine upgrade and design, not just for K-Star, but probably for example, Korean demo and other devices. So our development, I will discuss the details in the next slides, but here I'd like to just emphasize our development focus. Our first focus is the digital twin to integrate various fusion data in unified way. So to realize this fusion digital twin, we certainly need to integrate simulation code and data, and also experimental data, along with detailed model provided by this formatted CAD data. And then we'd like to also focus on enhanced three-dimensional simulation and analysis capabilities based on this developed digital twin. And by doing this, we'd like to bridge machine operation, experiment, and simulation in flexible and seamless way. So in the second part of this talk, I'd like to discuss some enabling technology to realize this kind of targeted fusion digital twin. So first one I'd like to explain is dedicated data framework that we are developing for this. And this is truly the key for the integration of various data that needed for this digital twin development, and which should provide a unified way to access various legacy formatted data, for example, like MDS Plus that K-Star is still utilizing. And we are employing this IMAS data ontology to access and make uniform interfaces for those kind of legacy data. And also we utilize HDF5. And this shows the rough schematics of digital twin data server that we are developing with many stacks and layers. I don't want to go to the detail of this, but for example, some notable feature is we are using this JSON technology to take any formatted data in flexible and a controllable way. And also we are utilizing this TCP/IP, for example, protocol to ensure good data integrity for real-time data that's streaming from this machine operation, for example. Okay, second technology that we'd like to emphasize is capability to this unified CAD model handling. So starting from this original CAD data with every nitty-gritty details of all those engineering entities, we usually do not need those kind of all engineering details. So we perform certain defeaturing to lighten this model complexity, but still retaining key engineering features for this digital twin development. And then that defeatured model is shared for the visualization and rendering, and also for this mesh generation and management. This mesh is, I will explain in later pages, but will be utilized for data analysis and also some parallel simulation after proper refinement and partitioning for the parallel simulation. And I'd like to emphasize that this mesh technology is actually the key for the integration and analysis of fusion data on engineering relevant model. And so a little bit detail on this mesh technology that we are using. We rely on a couple of different mesh technologies related, but slightly different. And for versatile, the mesh related capability, we utilize this open software, Open Cascade for CAD format conversion and mapping, and Gmesh for the mesh generation for simulation and analysis. And for kind of heavy lifting, we also utilize parallel mesh technology developed for US SciTech projects, so-called PUMI, developed by Scorec team in RPI. Key features such like the unstructured triangular mesh for arbitrarily complex shape discretization and various tools for parallel partitioning and the load balancing for supercomputing simulation, if it is required. And another the important element we are developing is a three-dimensional analysis algorithm and the library. For example, this kind of 3D collision detection and analysis of this dynamically moving inside this Tokamak device, like particle, ray, or sometimes static, but with complicating structures, magnetic field. Again, I don't want to go to very detail how we are implementing this algorithm as a library, but basically we are focusing on the acceleration of those kind of the collision detection of this dynamically moving object onto the static machine component with very complicated engineering detail. And this library is being developed as a general C++ library, which can be utilized in the different code as a third-party software. And I would like to emphasize that this actually algorithm and library help a lot for the development of the various 3D simulation and analysis code that could be well suited for this kind of virtualization. And here I'd like to list a couple of three-dimensional simulation and analysis code that we are developing for this Fusion Digital Twin. For example, we are developing this kind of the full three-dimensional Monte Carlo MBI simulation code, so-called NUPDEC, for three-dimensional tracing of fast ion losses, and also this kind of the shine through for unionized fast neutral particle. And also similarly, we are developing the RMP-induced three-dimensional magnetic field tracing code, so-called POCA, for this kind of the purposes. I will show some example of the application of those code in virtual case study in later pages. And the other category of code we are recently very actively developing is synthetic diagnostic code based on detailed three-dimensional CAD model of Tokamak. For example, this one shows the development of this synthetic Lyman alpha diagnostic for a neutral particle actual diagnostic in K-star. We are developing this synthetic three-dimensional Lyman alpha diagnostic code in parallel with this actual diagnostic the system installation in actual K-star. So we hope to utilize both of them in coming years soon. And the other element, the technological element I'd like to emphasize is this visualization client based on game graphic engines. So in our development, we utilize two popular graphic engines. One, the Unity, which is commonly used for the development of actually computer game for mobile device. So we are utilizing this particular graphic engine for real-time processing capable visualization client, which is suitable again for either laptop or mobile device with relatively the light computing resource. And the other graphic engine that we are utilizing is Unreal. It actually provides very high quality photorealistic rendering of complex object. And this one we utilize for the development of the application for time-consuming analysis and simulation, namely that does not require a really fast, the visualization or interactive, too much, the computation in some sense. But of course, again, this Unreal graphic engine requires really powerful computing resource. And the final entity I'd like to briefly introduce is the component or the technological element to connect this data server and this visualization client made by this the computer graphic engine, game engine. So we call this component so-called a virtual Tokamak control center. So basically, this is controlling the connection of data server and the visualization client via socket communication. And this actually is it can be seen as a application, either application or the library. Actually, it also provides assets and tools for easy customization of user interfaces using Python. So for example, if we design the user interface for the connection of some simulation into this virtual K-star, we usually work on this kind of left panel, this type of this interface, and then it pops up when we actually run that application in virtual K-star, like this right figure. So now I'd like to briefly summarize what I have discussed, the partial summary. So we are developing this virtual Tokamak platform developed by this enabling digital twin technologies. So this figure shows the rough schematics of how this virtual Tokamak platform is organized. Basically, it takes basically at the bottom, the block is this virtual Tokamak server taking data from K-star in various legacy format, and then it connect those data in user selected way to dedicated supercomputer for heavy simulation, and then this process data will appear on this virtual Tokamak client based on this game graphic engine. So utilizing this platform, Fusion device can be virtualized in multiple ways. Actually, that's what I'd like to emphasize, according to selectively choosing or combining those enabling technologies. And various Fusion simulation and analysis code can be combined or integrated into this underlying data flow with this dedicated computing resource. I'd like to again emphasize. So now let me move on to this third part, the implementation of virtual K-star based on this digital twin technology that we are developing. So virtual K-star comes in two different actually operational modes at current implementation. First one is so-called real-time monitoring mode, and its virtual client is basically written in Unity. So this is dedicated for real-time processing of the real-time streaming data from actually operational machine. And the purpose is the real-time three-dimensional monitoring of K-star machine operations. So this page shows the example of how this implemented real-time operation mode of virtual K-star looks like. We can selectively choose which component will be virtualized or which one will be removed from this particular the implementation. It can be user selectively, the customizable, and and also it can provide various the different viewpoint and in somewhat computer game-like way. And the key, the important thing is it is providing basically this virtual the image of this real-time Tokamak operation. But actually beyond that, the various machine information is actually added into this virtualization. For example, probably flashing on this previous movie, maybe not very apparent, but for example, in this particular virtualization, this blue color tiles actually tiles with the thermocouple installed on the back plate of those tiles. So basically it measures the temperature of this first fall during this K-star operation. Actually, this virtual K-star takes all those data and selectively shows upon the user's the choice. For example, this kind of the temperature pop-up can be made just by hovering the mouse interactively on this virtualized environment. And as can be, I mean, as is apparent on these other two figures, real-time E-field equilibrium is also constructed and visualized on this virtualized environment during this real-time monitoring with this X-point location and also diverter strike point. So all those information can be virtualized and monitored in this environment. And alongside it, this rather comprehensive monitoring of this overall, the Tokamak the component surrounding this plasma. Also, we can selectively choose certain dedicated component if we really want to focus on the monitorings. For example, right one, it flashes so fast, but let me repeat this. So this left one is the virtualization, specific virtualization of the central solenoid coil of this K-star. And this right one just shows this in-vessel wall, inner wall, and this real-time E-field reconstruction. So now let me move to the other operational mode of this virtual K-star, so-called post-analysis node. This is written with this Unreal, the graphic engine, for simulation and diagnostic, the data analysis, which require rather long time processing. So not doable in real time, but with some kind of the batched or the a little bit time-consuming way. But it provides integrated visualization and three-dimensional data analysis. So complex various fusion simulation can be integrated into this virtual K-star, employing this bottom, the figure representing automated simulation data flow with this dedicated supercomputer. So for this particular example is a three-dimensional simulation of NBI fast ion, their orbiting and losses on first ball component, etc., etc. And I'd like to emphasize that this capability is quite well suited for the high fidelity simulation requiring high fidelity machine detail and the engineering relevant the analysis. So this page shows, for example, one such yet another example. So this figure shows, this snapshot shows the 3D particle tracing and the mapping of this RMP, the resonant magnetic field perturbation, which is truly three-dimensional, induced field line splitting and resulting heat flux pattern on this diverter plate on this K-star. So we can see these highly non-trivial structures of this field line splitting and then resulting highly anisotropic the distribution of heat fluxes on this the diverter plate. All this kind of analysis can be done with this end visualization and analysis in this virtualization environment within virtual K-star. So let me move to the final part of this talk, ongoing and future works that we are in this day working on. So the first one I'd like to introduce is automated experimental the data analysis within this virtual Tokamak framework. We are now developing and integrating Bayesian integrated data analysis capability into this virtual Tokamak framework for more reliable and robust profile reconstruction by combining multiple diagnostic for certain targeted physical information. For example, this slide shows our recent development of this Bayesian IDA for plasma density reconstruction, combining Thomson scattering, two-color interferometry, and the beam emission spectroscopy. This kind of reconstruction, depending on the model detail, actually takes some computing resources, but this automated data flow provided by this virtual Tokamak actually enable the kind of the calculation and integration of that calculation rather seamlessly into this platform that I'd like to emphasize again. And certainly we want more three-dimensional simulation and analysis capabilities. So we are actively developing high-fidelity engineering and the physics simulation code, along with synthetic diagnostic based on CAD model. So for example, on this left panel, shown is the high-fidelity supercomputing simulation for eddy currents with very detailed CAD model in a scalable way, employing fast multiple and the hierarchical matrix the techniques. And also we are developing whole device, the gyrokinetic code that can take detailed this wall geometry, utilizing the unstructured mesh that I have mentioned before. And this right figure shows yet another example of three-dimensional analysis capability that we are developing. Synthetic ECEI diagnostic or turbulence the study. So in KSTAR, we have very powerful three-dimensional actually ECEI diagnostic capability. And now we are utilizing this kind of three-dimensional the code development technology to actually generate this turbulence data from high-fidelity gyrokinetic simulation code, and then converting that simulation data into the synthetic ECI image for more accurate and the systematic simulation, validation study, and also analysis of those measured fluctuation from ECI diagnostics. And last thing, but not last but not least, I mean, probably perhaps the most important in the coming years is our effort for the evolving this platform as a the platform for AI-based various technological development. I'd like to emphasize that digital twin is actually a very natural platform to develop and integrate AI-related the models, since digital twin actually provide very natural three-dimensional integrated data platform, and that can be utilized for various AI model and technological advancement for advanced diagnostic and the control that can be deployable to actual machine operation. So we are now focusing our effort for the development of interfaces, actually as a starting step to connect the plasma control system simulator that's being utilized in KSTAR, that's so-called TOXIS, with this virtual Tokamak platform. And then eventually we'd like to make this virtual Tokamak platform equipped with AI for this kind of virtual control experiment in coming years. So this brings me to the final page, the summary of this talk. We are developing key enabling technology which are derived for the realization of fusion digital twin. So technologies like parallelizable unstructured mesh, algorithm for three-dimensional analysis, and graphic engine based on this game technology. And utilizing and combining this enabling technology, we are developing the virtual Tokamak, I mean, targeting this virtual KSTAR for real-time monitoring of this KSTAR operation by using this real-time operation mode, and also the post-analysis mode virtual KSTAR, aiming three-dimensional fusion simulation and analysis. And many potential and possibilities are ahead. I'd like to emphasize AI-based control and design, though not mentioned in this talk. We are also thinking CAD-based simulation for machine design in future. So that's what I have prepared, and thank you very much for your listening.
So thank you very much, Jae-Min. So very impressive talk for the development of the digital twin in KSTAR. So now open the discussions if you have questions, please raise a hand or write your question in the chat. Okay, so Federico, go ahead.
Yes, thank you, Jae-Min, for the interesting talk. Just a technical curiosity. What is the requirement in terms of computational research to run this digital twin, to run, for example, the virtualization of the Tokamak and other features of your digital twin?
You mean I don't think I fully understand your question. You mean the technological kind of the skill to develop this, or I mean,
No, for
could you
example,
please repeat?
yes, for
Mhm.
example, you made us note the virtualization of the Tokamak, no? This 3D model that you can explore within the vessel. So I was wondering if this service is run, for example, on an HPC, and you have to connect from your laptop, or and if there are some resources requirement for the computational resources.
Oh, yeah, okay. And now I got your question. So probably let me explain that using this, for example, pages. So okay, yeah. So the virtualization itself, or the graphic rendering of those data and the machine detail, that does not require actually supercomputing capability, but still, of course, require a very decent the rendering capability. So we have a dedicated GPU server, probably not powerful or big to be called a supercomputer, but still with very strong GPU, the computing capability. So this actually server provide all this kind of rendering, and then user utilize their either laptop or personal computer, connect to that server, and then receive this kind of visualized or rendered graphic image. And but that's just the rendering part. But all those necessary simulation or analysis, something can be relatively straightforwardly done within this the relatively medium GPU equipped server, but some of course require dedicated supercomputer, require a lot of the computing resources. So we have yet another very big computing resources attached to this computation or data flow. Is really supercomputer. So we have this kind of a little bit different server working behind this user interface.
Okay, I see. So basically, you need a dedicated machine for some of the services.
Yes.
Okay, thank you very much.
Thank you.
Okay, so now we have the 3 questions from chat.
Mhm.
First question from the Christians. What are real advantage of such a technology for improving the understanding of the complex plasma simulations?
Oh, yeah, this is a good question. It depending on the actually simulation topic. So I think that not every simulation can be benefited from this kind of 3D or virtualization. Obviously, some simulation just want to predict, for example, one-dimensional profiles, evolution of plasma. Certainly, that does not require this kind of the heavy, the virtualization or three-dimensional processing. But actually, the particular example shown in this page is a good one, I think. For example, we want to analyze very detailed the impact of subtle three-dimensional features of this Tokamak plasma. For example, of course, Tokamak plasma is basically axisymmetric one, but due to the complex shapes of this plasma facing component, for example, or added three-dimensional complexity, for example, this resonant magnetic field perturbation, which is imposed, for example, controlling purpose of this plasma performance to avoid LM instability, for example, in H mode. In those circumstances, actually, the plasma response is highly non-trivially three-dimensional, and their interaction or impact on this machine detail is something the actually fusion engineers are deeply interested in. So for those kind of problem, I think this three-dimensional platform actually provide very good the actually tool for the various kind of the analysis and I mean the engineering development. So
maybe I can just jump in very fast. Okay, this is true, but at the same time, you can also do similar visualization just using ParaView, and this has already been proved with the direct code. If you check the paper of Sarkimaki of 2 years ago about the heat load due to runaways electron expulsion to ether wall, we basically did very simple visualization using just ParaView.
yeah, so I don't I mean kind of I'm not saying that existing tool cannot do this kind of thing. What I'm saying is those kind of capability can be integrated as a kind of the I mean, how do I say, coordinated research tool on this single platform. So, I mean, certainly ParaView can provide a nice three-dimensional rendering of those kind of simulation data. Sure.
Okay, thank you.
Okay, so second question from chat. So from the Pretty, how do you validate the digital twin model in terms of the accuracy?
Yeah, that's a really good question. That's actually something we'd like to actually learn and say in future. For example, again, I would focus on this page or probably some others in shortly. So, for example, this kind of very detailed three-dimensional the analysis and I mean the recorded result of this three-dimensional heat flux pattern on debutter, they should be actually measured and compared with the simulation result. That's a really good question. And usually for this kind of three-dimensional or this highly non-trivial heat flux pattern analysis, we usually rely on this. I'm actually diagnostic expert. I'm not the diagnostic expert, but this various kind of visual image, for example, and that image data is actually sometimes cannot provide enough resolution actually for those kind of information. So, but those kind of comparison and validation actually not just the development of this kind of sophisticated three-dimensional analysis technology in terms of the digital twin, we also need the advancement of this more precise and high resolution diagnostic, I think. Yeah. But I think, for the others, for example, simply there are the unanalyzed data. For example, that's something very interesting thing is something. For example, yeah, we recently noticed that during this low target density operation, we sometimes see this overheating of the certain component of this the pipeline or various thing beyond this beam armor. We first a little bit curious and puzzled what is causing that, and eventually, actually very shortly we realized that that's due to this shine through, and this kind of three-dimensional analysis capability provide actually direct the analysis result of those kind of things.
Okay, so is it fine to Pretty? Yeah. Okay, so then the last question from chat from Melby. What features are you presently using in the control room during K-star operations? Who would be the users of these tools? How do you approach user training?
That's a really good question. So for this, for example, this real-time monitoring system, we just started utilizing this and tried adding the new features according to actual operators' need. For example, this capability for this extended tracing of this equilibrium up to the virtuous strike point is something upon this request from the operator. So there are the machine operators actually looking at this the real-time operation mode of virtual K-star during K-star experiment, for example, for this more intuitive and three-dimensional the monitoring of this first fall temperatures. So before implementation of this, the first fall temperature was just monitored by looking at this kind of the Excel spreadsheet type of this two-dimensional array. So usually without this expert kind of training, it is hard to know which one corresponds to which, the position of this three-dimensional, the inner wall. But this kind of capability provide direct, direct interpretation of those kind of information. So this is actually a procedure that we also making something and learning and modifying that kind of feature, but we try to add more feature according to users' need. And according to the question of this this training, actually, for the K-star operation, actually, there are some engineers who are actually not very familiar with this fusion, but just put for this machine operation, for example. Those kind of the machine operator, actually, this kind of virtualized and three-dimensional the monitoring system actually provide actually a faster way to learn about this machine. So we think that's one of the good features of this the system. And for this the so-called post analysis, actually this is for mostly currently for the researchers. For example, this capability is now utilized by these RMP researchers, for example, who have fully, the trained and also expertise on this running this sophisticated code. But that's a good point. Eventually, we'd like to make this analysis tool more user-friendly and something that can be usable without too much detailed knowledge on this plasma physics in coming years. So, but that requires also a lot of learning and the redevelopment of some features, I think. I don't know whether I gave enough answer to the question.
Yeah. Okay, so finally, I have very short questions. So in last slide, you pointed out in future you have the plan implementation of the CAD-based simulations. So what do you mean the CAD-based simulation? So that it's using the ANSYS or the SolidWorks or something, or just to simply use CAD mesh?
Just CAD for the actually not existing one. The last the line, what I mean is the CAD-based simulation for machine design. So for certain machine design, for not existing machine, just in the design phase, we'd like to utilize that machine design for actually CAD-based engineering relevant level of plasma simulation, for example, for the validation check of that design, utilizing this whole capabilities. So that's what I mean.
Okay, so thank you very much. So
Thank you very much.
Another question in chat. So if you have time, please give the answer
no
in
problem.
the chat window.
Okay.
Okay, so thank you very much, Jae-Min. So
thank you.
Then we want to proceed to the next talk from the Miquel Moreto.
Hello, can you hear me?
Hello? Yes. Yes, it's perfect. Please go ahead.
Okay, so thanks a lot for the invitation to this workshop. My name is Miquel Moreto, and I'm an associate professor at UPC and also team leader at the Barcelona Supercomputing Center. And today I'm going to explain a little bit
the last years working towards European HPC accelerators based on the RISC-V Open ISA. And I think I hope that this is very interesting for all of you. Before starting, I would like to give a very quick overview of BSC. BSC is a National Supercomputing Center in Spain. It's a public institution that has a very big machine. This is Milestone 5, our current supercomputer, above 300 petaflops. And as I said, it's a public institution, which means that many European and worldwide researchers are using these machines. And it's Milestone 5, which means it's a fifth generation of Milestone. And probably you have seen this photo. This is Milestone 4, which is in the chapel that Eddie at the beginning said, mentioned the Dan Brown's novel. And basically the action of Dan Brown's novel is happening in this very unique location for a machine. So this is a real picture. Nowadays we are installing a quantum computer here. So next time you come to Barcelona, please stop by and visit our chapel. BSC has been growing very quickly for the last 20 years when it was founded. We are right now close to 1,200 people, so really big facility in Spain. And this is our building. So if you come by, as I said, you have to come and visit us. Basically, there are four research departments at BSC. Life science, earth science, and case. These are application departments, which means that they are developing new applications and new models that are run on the Mare Nostrum supercomputer. And in particular, in case, we have the group of Mervi, who is working intensively in fusion research and developing new results there. In my case, I am from the computer science department. This is a very unique department. We are 400 people, and basically our goal and ambition is to develop the next generation of supercomputers, both at hardware and software level. So how are we going to do this? I mean, first of all, I mean, you have to realize, I mean, that developing a supercomputer is really expensive and it's very difficult. It requires a lot of time. And our current strategy is based around the Open ISA, the Open Instruction Set Architecture RISC-V. But before that, we were working on a different strategy. In fact, for over a decade, BSC and the European Commission was promoting a lot the ARM ISA. ARM is a British company, headquarters in Cambridge. It is a proprietary ISA, so they define the instructions that are executed on the hardware, and they basically sell this definition to implementers, or they also sell IP where they implement themselves the processor or the accelerator that is based on the ARM ISA. 15 years ago, when we started collaborating with ARM, basically in the Mont Blanc projects that you see here, basically we had that ARM was a European company with a very promising future, and BSC selected this ISA and Europe in general as the European ISA to build HPC systems. In this time, we developed several prototypes. Have in mind that 15 years ago, ARM was an ISA for mobile phones, for embedded systems, so it was not an HPC ISA, so it was not especially developed for HPC. So we had to put together prototypes to design, to develop the software ecosystem. So this is here on the left, you can see the first ARM-based HPC in the world that was developed and deployed here at BSC. It used to be in the chapel. Nowadays, it's in the museum from BSC. And this is very important to have this small prototype. It's just 2 racks because it allows users to develop all those systems software. This includes also the applications, operating system, compilers, all the things that you need to run an HPC efficiently have to be adapted to new ISAs. And this rack was really important to do that. Then what happened? So basically, around 7 years ago or a little bit more, there were some problems. Basically, there was a political problem, that is the Brexit. Then it meant that the UK left the European Union, so it was no longer ARM was no longer a company from a European country, from a country from the European Union. And what is worse, I mean, there was a company called SoftBank that acquired ARM, that is a Japanese company. This allowed Japan to really implement the vision that we had here at Europe, to develop the fastest supercomputer on Earth back in 2020. You can see it here on the right. So this is the Fugaku supercomputer that was deployed in 2020 with over 400 petaflops. So I mean, this was a really big machine. And the development of this machine costed around 1 billion euros, or 1,000 million euros, spread over 6 years. So this was very good for Japan, because I mean, they developed an impressive machine and an impressive system that was the top one in the world for many years. Still, at BSC, we kept lobbying to have domestic technology. We want to have European technology for HPC. So this is Mateo Valero, our director, who has been promoting ARM and now RISC-V to develop HPC systems in Europe. And also the politicians. You have some quotes here from Jean-Claude Juncker and Ursula von der Leyen. And basically, they were saying that without chips, there is no digital. So you need these chips to run your Fusion applications or whatever applications you want to run. And basically, that motivated the European Chips Act, that is funding with 40 billion euros all these developments. In particular for HPC, what was a very important turning point is that it was the creation of the Euro HPC joint undertaking, and this is a new institution that is in charge of funding the acquisition of HPC systems. So, for example, Maelstrom 5 is a European machine. It's a European supercomputer that is funded by the Euro HPC joint undertaking, together with some national governments. And the second thing that Euro HPC is doing is developing HPC technologies in Europe. And you can see here in the picture in the middle that all the European countries are basically in this joint undertaking and are promoting HPC technologies in Europe. So with Euro HPC and with the acquisition of ARM by SoftBank and Brexit, we had to look for a new strategy. And basically, what Europe has embraced is the use and the adoption of RISC-V as the European ISA. So right now in Europe, we are following this philosophy of build versus buy. So trying to design, verify, and fabricate our own chips and systems, with the idea to have in 5 years maybe, or a little bit earlier, some European supercomputers in the top 500 lists that are based on European technology. With this, what we will, so our ambition is to transform this HPC stack that you see here, that you basically you have that all the applications, the libraries, operating system, compilers, everything is open except the hardware. And with this revolution of the RISC-V ISA, we are hoping to have a full open stack that is based on domestic technology. Then here, this is a very important slide. This is the technology roadmap that the European Commission is promoting for HPC. Basically, you can see here that back in the end of 2018, in fact, we started the European Processor Initiative, the first phase of this project, that lasted 3 years. And after that, there was a second phase that is developing these European chips that I will explain later. And in parallel with the second phase, you can see on the top the EU pilot and the EUPEX. So these are 2 pilots that are taking the technology developed in EPI and building some racks, some systems, some real systems at scale that are first demonstrators in order to develop later an exascale system. And I will also cover a little bit these new projects that are funded by the EU Chips Act that will keep promoting and developing European technology for HPC. This is the DARE project. So let's start with the European Processor Initiative. Basically, this is EPI is a framework agreement, a framework partnership agreement. It's a flagship project from the EU. It's basically close to 30 European partners that are in this project. There was a first phase that was an 80 million phase project, and then a second phase with a budget of 70 million. And basically, we are at the middle of the second phase. So AGA1 started at the end of 2018, finished in 2021. AGA2 started just afterwards in 2022, and will finish at the end of next year. What are we developing in EPI? Here, when we started in 2018, we decided to follow a strategy with two designs. One that is a general purpose processor. It's the REA chip. This is an ARM-based system because basically for many, as I was explaining before, for many years in Europe we were developing ARM-based systems, and we were at a point that a company called Cyprel was able to take all this knowledge that we had acquired and develop this GPP, this general purpose processor, based on ARM. And in parallel with this design, this was for the short-term delivery of an HPC system that is European. And for the long term, what we decided to develop is the European Processor Accelerator, which is a more academic design with many academic partners and also companies that you can see on the right, that was developing future accelerators to be deployed a little bit later than REA. REA, here, I mean, you can see a summary of the key features that is included in this system. Basically, this chip is going to be submitted for fabrication this year. Cyprel is the company that is taking full responsibility of the development, verification, and preparation for fabrication of the design. And basically, before summer, they announced that this chip will have 80 ARM Neoverse V1 cores. So Neoverse cores are designs that are licensed by ARM. So ARM, as I said before, can license the architecture specification, and then the company can implement their own cores. That's what Apple and Samsung and others do, and Fujitsu. Or they can license a specific design, like the Neoverse cores. This is what is in this is something that, for example, Amazon is doing, or the NVIDIA Grace also has some Neoverse cores. So Cyprel followed the same approach. They licensed this core design. They integrated a very large chip because 80 cores is really big. And they have support for HBM, high bandwidth memory, and also DDR memory. So this is going to be a really interesting system, and with a lot of performance that will be available next year. So this is, I think, very good. But what we were more excited, in fact, that's what BSC was coordinating, was the development of the European accelerator. And here you can see a block diagram of what we have. Basically, there are at the bottom 3 different accelerators. One that is the vector accelerator that we are contributing to. Then there is a stencil accelerator for AI applications, and then there is a variable precision accelerator that was developed by CEA for other applications. And these accelerators are connected with a network on chip, and they have a shared last level cache. This design is developed, as I said, by close to 10 different partners, so each partner is developing a different piece of this accelerator. In our case, what we think is more interesting for traditional HPC and also AI applications is the vector accelerator. Here we are collaborating with the Semidynamics company that is developing the RISC-V core. This is Avispado on the left, is a traditional segmented pipeline design based on RISC-V 64-bit ISA. So this is the general purpose core that is running the vector accelerator. And on the right, you can see a summary of the key features of the vector accelerator. What is different, the key difference of this accelerator is that it is a long vector accelerator. What do I mean by long vector? So normally, if you check x86 systems, normally they have ARM and they have vector units like AVX 512 that are 512-bit wide. And this means that for double precision operations, you can fit 8 elements per vector. In our case, we are doing a much longer vector. It's a vector of 16,000 bits that can fit up to 256 elements. So this is similar to what Cray was doing in the 80s. So it's a long vector approach, and also what NEC with the Aurora design is doing. So we have really long vectors that can be very powerful for HPC applications. And this is what we started developing in 2018. And since then, we have done 2 test chips that you can see the floor plan here in this slide. On the left, the first test chip that was done in 22 nanometers, Global Foundries, back in 2021. It has 4 cores with the 4 BPUs and 2 stencil accelerators and 1 variable register accelerator. You can see the blocks here on the left. And then 1 year and a half later, basically we respin this design, same technology node. You can see it on the right. We improved performance features of the design, and in the end, we have this. We have 2 cores instead of 4. We have 2 cores with the BPU, much higher performance from both of them, together with the other accelerators. This was fabricated. In fact, if some of you are attending SC this week, we brought one of the chips that is doing a demo in our booth at Supercomputing. And basically, this chip is stable. I mean, you can run Linux, you can run HPC applications on top of it, and it is stable. It means that it runs for days. I mean, it doesn't. I mean, it's a high quality chip. The first one had more difficulties, but the second one, I mean, it's really stable. So this is what will be the final. It's the final chip that was on in EPI, but in EU pilot, this is the pilot that is trying to develop a small rack based on the EPAC technology. We are going to do a third iteration of this accelerator. I'm going to explain the details next. So this is, as I said, this is a project that is trying to demonstrate technology for pre-exascale system. So, and this is based on the EPI technology and is running in parallel because we are trying to integrate what is already available and developing new IPs. Here, you can see on the left the chip that we are going to fabricate next year. Basically, we will have 2 different chips. One is the Beck chip, and then the other one is called the machine learning chip. I'm focusing on the Beck chip because this is what BSC is developing. But if you have interest about machine learning, we also have a chip that is specific for that. And in this chip, we will fit 8 cores. That you can see 4 cores with the BPUs on the top, 4 cores with the BPUs at the bottom. And what is really interesting is that here we will already have some DDR controllers, so we will have high speed memory connections. The previous tape outs, the previous chips didn't have these controllers, so they had to use an FPGA to access memory, which limits a lot performance and bandwidth when accessing memory. But this is something that will be fixed in this EU pilot chip. Basically, we will fabricate this chip in 12 nanometers Global Foundries, And we will put together the European accelerator module that you can see here, where we will have in the middle this vector or the machine learning chip connected with the low power DDR chips that you can see here, and then you will have a small board that includes this chip with the 4 LPDDR modules. What are we going to do with that? So we will take 8 of these EU Pilot accelerator module, and we will build the EU Pilot accelerator system that you see here. So this EAS. And basically you can see all the modules here that will be connected, and then we will have a connection with PCI Express to a host system. This host system can be a traditional x86 machine, or maybe the EU Pilot, the EUPEX REA chip that is being developed in parallel. So this is what we will be delivered, and with that we will be able to have a rack, a full system, a small size system that demonstrates this technology. And it's not only that we will be contributing to this EU Pilot chip, but also there are, well, what I mentioned about EPI, EU Pilot, and there are other European projects like eProcessor, where we are contributing also with the vector accelerator from BSc and IPs from other partners in Europe. Then what's coming next? So there is this project called the Digital Autonomy with RISC-V in Europe. So this is basically a new framework partnership agreement. So it's the follow-up FPA of the European Processor Initiative. It's going to be a 6-year program with close to 240 million of investment with national matching funds. So this means that the countries, each government has to co-fund 50% of this funding. And basically here in this DARE project, we are going to put together the HPC centers that are in Europe, and these HPC centers will define the requirements of the exascale systems that they want to have. And basically there will be software and hardware partners developing the full stack for HPC, as I was mentioning at the beginning. We want to go from the applications down to the hardware, make it open and domestic. Right now, this FPA, the DARE FPA has been awarded some months ago, and we are 40 countries from 13 different 14 partners from 13 different countries. And basically what we are going to develop is what has been defined in the first SGA. SGA is the first phase of the project. This is basically BSc is coordinating this project. Then there are ULIC Supercomputing Center and BSc that are defining the software stack and the applications. And basically there are 3 companies from Europe, Codasip, OpenChip, and Accelera, that will develop 3 different systems. Codasip will develop a general purpose processor based on RISC-V, targeting HPC. OpenChip, together with BSc, will be developing a vector accelerator targeting traditional HPC. And finally, Accelera will be developing an AI inference accelerator, also based on all of them based on RISC-V. And IMEC is going to help with the integration and the physical design of the chips, with the idea to have a production run of these designs by end of 2026, maybe early 2027. This SGA1 proposal was submitted in September. I believe that last week we received the good news that it's going to be funded, and this means that we expect to start early 2025 with the project. Hopefully in February we will be starting with this first phase of the DARE project, and developing these 3 designs that I mentioned here. Okay, then in parallel, in BSc, we have been working on many different RISC-V projects. As I said, we are trying to develop this full open stack that goes from the application down to the hardware. And basically, you can see here a list of projects that are developing RISC-V technology. It's not only hardware, but also software, not only HPC, but there is also many projects with automotive applications, space applications, embedded applications, and also the hardware. And basically, you can see here, EPI was the European Pressure Initiative that I already mentioned. We also have EU pilot and also DARE that will be starting soon, as I already described. So these projects are developing RISC-V software and hardware. So to develop hardware, I mean, it is something that is very important and it's also very unique. So at BSc, we have put together the usual design methodology that are in companies where we devise an architecture. We simulate this architecture, the design that we want to implement and fabricate. Then the RTL teams implement this architecture. There is a verification team that takes care of verifying that everything is working as expected. These IPs are integrated in a system on chip, emulated on an FPGA, and finally fabricated after doing the physical design tasks. This flow is basically implemented by each step in this flow is implemented by a different group. And right now at BSc we have over 100 hardware engineers taking care of implementing the different designs that we are doing. And it's not only the contribution to European projects that I described before, but also we have some internal academic cores that we call Lagarto. We have 4 different generations of this Lagarto cores that we are integrating with our vector accelerator and building a multi-core using the Open Python Open network on chip. So this means that we have done also our own tape outs. Here you can see the 4 Lagarto chips that we have developed. The first ones were very simple. The performance was not very high because we were starting to do our own chips. Now, the last one that we had that we have fabricated is Chameleon, and this one already has an out-of-order core with some custom accelerators for different application domains. So this is starting to get higher performance and more efficient execution of applications. And basically, what we are right now fully focused is in this Barcelona ZetaScale project. This is a really big project that is funded by the Spanish Chips Act that is called PERTE chip. So I mentioned that Europe has put together a European Chips Act that has over 40 billion euros to fund the development of domestic European technology. At the Spanish level, there is a similar program that is called the PERTE chip that has a total funding of 12 billion. So this is really big project. And basically one of the first projects that started in this PERTE chip is the ZetaScale project. And basically it's a collaboration with Intel where we are developing a RISC-V general purpose. We are developing the BPU accelerator that I mentioned before and the cache hierarchy to have a full BSc HPC multi-core design. And we are going to fabricate this chip in advanced technology node. Basically, Intel IFS, Intel Foundry Services, is going to provide is going to take care of the fabrication of this chip, and they are also adding many technology-dependent IPs like the memory controller, PCI Express. So this is something we are very excited about. We think it has a lot of potential, and basically right now we are finalizing the first test chip of the project. This is a block diagram of what we are doing. I mean, I cannot share too much. I cannot share many more details, but basically what we have is that BSc is developing here in the middle the CPU subsystem with our Lagarto core, with the BPU accelerator that I mentioned, and the cache hierarchy from Open Python. So this is what goes here in the middle, and then Intel is providing the rest of the system on chip. So they provide the DDR memory controller, the peripherals, the PCI Express, and basically the goal is to submit this chip for fabrication next week, and to have early in 2025 the boards and the packaged chips so that we can test the performance of our applications. And not only this, but also next year we will do a second iteration of this design with more advanced features in our design, and also in hopefully in collaboration with OpenChip. OpenChip is a spin-off that BSC created 3 years ago, and OpenChip is the company that I mentioned that is the responsible of developing the vector product in the DARE project. And so they are going to help us in productizing, so bringing to market these technologies, so that maybe in 3 or 4 years we can see here in the chapel Manostrum 6 with some RISC-V technology. And that's all from my side. Thanks a lot for your attention, and if you have any questions, I will be very happy to answer.
Okay, so thank you very much, Miquel, for excellent overview. So recent activities. So we had already the several questions in the chat window. Okay, so then I will read the questions from chat. So first question from Luis. This is a very short question. So is Switzerland included?
Included in what? Sorry.
So Switzerland is partner or not?
Well, I described many different projects. Maybe I can go back to the slides. Maybe here in this chip, the stencil accelerator that you see here is developed by ETH Zurich. So Zurich is Switzerland, and Fraunhofer from Germany. In the EU pilot, I mentioned that there is this vector chip. There is the machine learning and stencil chip, the MLS chip. This again is developed by ETH Zurich. So they are both in EPI and EU pilot. When you go to there, here it is a little bit more challenging because here you see this the matching funds from the national government. I believe that in there, Switzerland is not matching the funds, and then there is the contribution of Switzerland is smaller, but still they are part. No, you see they are not part of there. This is because of the national matching funds that this is challenging, because if you have to co-fund 120 millions, I mean, this is a lot of money. So so Switzerland decided not to participate in there, but they are part of Europe and of the Horizon Europe program, and they have been actively contributing to this.
Okay, thanks. So next question from Federico. So I did not get if there is a plan to allow some preliminary test of the CPUs and accelerators you are developing. So would it be possible, and would you be interested in comparing the performance of your developments with other already available at the BSC or the somewhere else with standard or the fusion-oriented benchmarks?
So yes, I mean, as I said, I mean, developing HPC system takes a lot of time and it's very hard. At the beginning of the project, basically, in order to test our designs, we were doing simulations because there were no chips, there were no RTL, so we had to do some simulations. Then later, when we started implementing the RTL, we were able to do simulations using the RTL of the design. When this RTL was more mature and was capable of running on top of an FPGA, we were able to provide what we call a software development vehicle, an SDV, that boots Linux and runs applications. These SDVs are accessible right now. I mean, at the beginning of the project, were internal to the project. Right now, they are accessible to external partners that want to test RISC-V technology. And this is, I recommend, I mean, this can be requested, and there is a procedure to run with the FPGA. And finally, we have some chips. Again, I think we can run applications in these chips. I don't think we can share the chips with external partners, but you can collaborate with BSc people so that these BSc people run the applications with your assistants if you're interested, and then it's easier. So you have two options. Either if you want the ASIC, you need to collaborate with someone at BSc. If you want just to run on the SDB, you can request access and then you do yourself. Basically, it's an FPGA cluster where you request access and then it emulates it's like a regular HPC machine. You have a terminal and a Slurm, and then you can run things there. And we are very interested in getting feedback from external users to our design. So please contact us.
So thanks. So next question from the Christians. There has been an effort to bring the fusion simulation code on the GPU accelerators. What would be effort required to bring present fusion code on the new European RISC-V technology?
That's a very good question. I mean, and it's in fact more general. So we can develop a really, really good hardware and really, really good chips. But if there are no applications that are capable of running on top of these chips, they are basically useless. So it's very important. It's strategic for Europe and for us as BSc to, in parallel with the hardware development, develop also all the software stack. And we have been doing a lot of work on developing libraries, traditional HPC and machine learning libraries, so that they are compatible with RISC-V. We are also developing compilers, so GCC nowadays or LLVM works very well with vector extensions from RISC-V. So the software ecosystem is growing very quickly. That's what I would say. Having said that, in HPC systems, you normally want to fine-tune your application. You want to really get the last flop of your machine, and this requires time. And at BSc we have some centers of excellence. Well, it's not BSc; it's a European Center of Excellence that is adapting some of the applications to some HPC European applications to these accelerators. And I believe that there are some efforts with the fusion applications, but I'm not 100% sure. But this is something that has to be done now before the hardware is available, so that when the hardware comes, we are ready for that.
Okay, so next question from the Jeff. So how does your development path connect with the production of chips for the consumer market?
Again, that's a very good question. So BSc is a research institution, a public research institution. This means that we cannot sell the chips that we are developing. I mean, for the last 6 years, we have been designing, verifying, and fabricating test chips that are academic test chips, and we are doing this via Europractice in general. The Intel collaboration is different, and it's bilateral collaboration with them that we are doing. If we want to bring these designs to the market, we need a company that sells them. And our strategy right now is based on OpenChip. OpenChip is the spin-off of BSc that we have transferred the vector accelerator to them, and they are in charge of designing a product based on this BPU. We have also collaborated with other companies. So I mentioned in EPI we have an EU pilot. We are collaborating with Semidynamics, and basically they are a company that sells IP, and they can also bring this to the market. In eProcessor, I didn't cover it, but we are collaborating with a French company called CRATOS, so they can also bring these designs to the market. And in there, the big difference between there and EPI is that there is driven mostly by 3 companies. The 3 designs that we are developing, it's 3 companies that they must bring to the market these designs. So this is CODASIP for the GPP, for the general purpose processor, OpenChip for the vector accelerator, Accelera for the AI accelerator. And these companies will be the responsibles of bringing these designs to the consumer market.
Thanks. So last question from chat window, the question from the sharers. What programs are you using for the simulations of these tips? Can ordinary computers run these programs?
Yeah.
What do you mean by soon we will develop good chip? What is mean by good chip? What are features?
So again, that's also a very good question. So the first prototype chips that we built didn't have a memory controller, and the memory controller is what allows you to have lots of gigabytes per second of data from the memory to the chip. In general, HPC applications require a lot of memory bandwidth. If you don't have a memory controller, the performance of this chip when running production applications will be low. But this is the test chips we have done so far. In the EU pilot, the chip that I mentioned, the vector chip that I mentioned, has 8 cores and also has DDR low power DDR controllers, so that it will have a good memory bandwidth and latency. And this will be fabricated early 2025. So by the end of the year, we expect to have these chips and to build this system. So this is when I meant soon means next year. But this is still a prototype. This is not a production ready chip that can be deployed. I mean, production ready chip has to work 24/7 for 5 years or 7 years. I don't know. It has to work everything smoothly, perfectly. So normally companies do like different iterations of fabricating the chips and making sure that everything is in place. And the target for these production ready systems that are based on RISC-V technology are expected by 2028, 2029, based on European technology. Yeah, I'm referring. So in four years, we should have these big HPC systems based on this technology. Next year, we will have some small size pilots that show that this technology is working.
Okay, so we can accept the one more short question. So question from the remote participant. No questions.
Okay, then thanks a lot for your time. And if someone is interested in getting early access to this RISC-V technology, or you want to look at potential optimizations of your code to run on RISC-V HPC systems, do not hesitate to contact me, and we will be very happy to collaborate. We are collaborating with all over the world. We have collaborators in Europe, in the US, in Asia, in all the countries in the world. We are collaborating with them, and we would be very happy to do this effort to make sure that RISC-V is useful for HPC applications like the ones that you are developing.
Arkady Serikov from the Karlsruhe Institute of Technology in Germany. So if you can share, very good. So you have 20 minutes also for your presentation, including questions.
Can you see my screen?
Yes.
Full screen, right?
Full screen, yes.
Yes, so my presentation is about computational electronics analysis, interactions of deuterons with lithium target for fusion applications. So we'll investigate these processes for simple model to understand the physics behind these interactions. And then we apply our achievements and code developments for fusion managed in case of fusion material irradiation facility IFMIF-DONES, DONES-oriented neutron source. And then we conclude, and if some questions, we discuss parallelization and variance reduction technique of this run. So connected to previous speaker, I want to present Monte Carlo results conducted with MCNP code. So, as the previous speaker mentioned, this is analog of FIS code with a very long history of development, started from Manhattan project with very famous people like Neumann, Olam, Metropolis. And then after 70 years of development, we have version of MCNP 6.2, which combines most advantages development of physics, high energy physics, ion physics, whatever, and even activation calculations by Cinder library. And maybe somebody from these contributors to MCNP 6.2 will be famous enough, like people I mentioned before from Manhattan project, who knows. And when we apply MCNP for interactions of deuterons with lithium, we found in 1999, 25 years ago, that MCNP at that version 4.8 couldn't calculate accurately enough physics of deuterons with lithium. So problem was that it was very primitive interaction model, and it didn't consistent with experiments. So that's why it was a decision to develop a new extension of MCNP called MAC Delicious, Monte Carlo deuterium lithium interactions. Then in this century, MAC Delicious developed several versions, mostly concerning compatibility with new MCNP, and we have developed compatibility with Monte Carlo parallel computations, MPI and OpenMC. So we use updates of simulations and reactions, and we use new libraries for deuterium and lithium cross sections. So everything is listed in this slide. If you have interest, so you have some references provided for your attention. And we apply MAC-Delicious code to analyze basic processes for interaction with deuterium lithium. And in first part, I present simple model. And simple model is just lithium layer, like presented here in the yellow color, which is bombarded by deuteron beams. In this case, we have two beams inclined by 10 degrees to the normal, to the surface of lithium. And we have reactions of deuterons with lithium, and primary productions of neutrons, primary productions of gammas, and after that, neutrons can produce secondary gammas and secondary particles like alpha, proton, and so on. So what is important to understand is notion that deuterons release heating not on the front part of the surface, not on the front, but by some depth. So it comes to around 20 millimeter depth, and then release full energy. So that means deuterons stops almost at a distance 21 millimeter. So, and most energy released by break peak due to ionization processes. And as I mentioned, development of MAC-Delicious, we progressively improve neutron data interactions with deuterium lithium. And in this slide, we can see neutron source with angular yield. So in this case, we have forward directed yield of neutrons. So that means it's along the direction of neutron beam. And we can see that previous versions of McDaily could not describe well neutron yield beyond 40 MeV. And in contemporary irradiation facilities like IFMIF-DONES, the neutron spectra reached up to 55 MeV. So that means high energy range was not well described in McDaily. So that's why we developed code and use new deuterium lithium data to describe well high energy range. And then we apply this methodology to very simple model, which is basically cylindrical solid lithium colored in magenta in this left upper slide, which is placed in aluminum capsule. So, and we impeach this set by deuteron source on the left side, and the dimension of this deuteron source is 3 millimeter, like a disk. And if we have isotropic uniformly distribution of deuteron source, then we would have deuteron tracks in every direction with the same probability, uniformly isotropically, and it shows like a hemispherical distribution, and tracks are finished by the length around 1.9. So the break peak, there we have deuteron hitting the most, the distance around 1.86, something like that. And we have no any deuterons behind 2 centimeters from the source. But if deuterons direct monodirectionally, so if we have a kind of deuteron beam, the same size in pitch from the left to our lithium setup, so when we have more forward anisotropic distribution of deuterons, and the break peak at the same distance around 1.9 centimeter, and we have very few tracks behind 2 centimeter. And when we understand the physics of interaction deuteron lithium, and we apply our knowledge to fusion development for irradiation facility IFMIF-DONES. The program is very mature now. Currently, we have stage of design and engineering phase this year of water working package Euler neutron source right here in yellow line. And the decision of construction of IFMIF-DONES already signed, and it's already in progress in Granada. So VPNs is rather a large project, around 13 countries involved, a lot of resources arranged for this project. And we expect to run IFMIF-DONES for 30 years, and to get irradiation of structural and functional materials of future fusion power plant, like a demo type. So with energy production, so its ultimate goal is rather ambitious, I would say. About the model we are working for IFMIF-DONES, it's a very big facility, size around 100 meters length, with long accelerators, beam lines, and they heard the center of the DONES is deuterium lithium target. The deuteron beam impinge on liquid lithium, which is flow with very high speed, 15 meters per second. So then we created model shown on the left and right side, and we experienced very steep gradient around 18 orders of magnitude. So we use variance reduction technique actively. So the spectrum is very hard on area of deuterium lithium target, where we place high flux test module just behind the target with rather broad peak at 14 MeV, which is very important energy for fusion material radiation. And we calculated neutron and photon flux. We found that neutron flux is higher than photon, and we calculated deuteron energy deposition inside of lithium. We detected break peak at distance 1.86 centimeter from the front part of liquid lithium surface. So, and the important issue for this study is to keep distance between break peak with heat around 100 kilowatt per cubic centimeter to back plate by which the lithium is flowing. So this is only 6 millimeter between break peak and the back plate. So the thickness of the lithium flow is 25 millimeters. So we are very serious about accuracy for these calculations. And as I mentioned before, the deuterons energy attenuated like this from 40 MeV to 0 absorption on break peak. And we can recognize this peak on this profile. And we can check also the length of deuterons inside of lithium by stream code. But this is just a primitive estimate of the length of deuteron absorptions without any nuclear reactions of deuterium and lithium, without any neutron production or photon production, whatever, just to estimate the energy range. So this some details about deuteron beam profile and how this profile transferred to heat deposition with break peak, which is follows the curved surface of the lithium. So this is very precise computations because we are concerned about thickness of the lithium, and deuterons should not touch back plate made of steel. So this is point. So the heating should be removed by very fast moving lithium jet. So lithium jet totally remove this 100 kilowatt energy down to the quench tank located here. So this is a CAD model of target assembly. And to calculate neutron and photon heat deposition, we arranged MCNP mesh tally, covered this area of target assembly. we calculated neutron and photon depositions. Just to your memory, remember, so from neutrons and photons, we have around 20 watt per cubic centimeter. And from deuteron, we have 100 kilowatt. Could you imagine? 10 to 5 and 10 to 1. So 4 orders of magnitude difference between deuteron deposition and neutron photons. So deuterons dominate in heating in all components of test cell, and that's why I summarize power balance in this table. We can see the input power from deuterons 5 megawatt, and almost all of this power is released with deuterons in lithium. And neutron plus photon diffused all around in test cell components contribute only around 3% from this power. I just illustrate on here, and in conclusion of my presentation, I must say we have rather good achievements in code developments for deuteron lithium interactions at KIT. So, and we apply these tools and code development for MaxDelicious. This is current version, MaxDelicious 17, extension of 6.1 MCNP. So we use recent available evaluated deuteron lithium data, and we apply this methodology for simple model, as I mentioned before, with isotropic or monodirectional source distribution. So we have studied also these interactions for most important application for IFMIF-DONES, and we found that deuteron energy distribution is very important to calculate because of closeness to backplate, and we found that deuteron deposition contributes 97% of total heating in whole test cell volume. So that means this knowledge is very important. I hope I persuaded this point to all of you. Thank you very much.
Thank you. Thank you very much for your nice presentation. So if there are any questions, please raise your hand or put them in the chat. So I have I'm curious about this, the times for the calculations. How long does it take to do one of these calculations of?
Yeah, we use very promising and I would say important variance reduction technique developed just 4 years ago. It calls on the fly global variance reduction. So we follow every track of neutrons, and we can split and rotate particles very efficiently. So you see, with our development on the fly global variance reduction, we can reach 25-factor improvement in relation to most advanced version of MCNP realized in Advantage code, for example. So we apply this variance reduction for ITER, and it shows much faster calculation. Answer your question, so I would say by 2 days we can calculate neutron flux everywhere in ITER, for example. And for IFMIF-DONES, the same time, because size of test cell and ITER nearly the same. So I would say by 2 days we can calculate neutron fluxes, nuclear heating, and some responses necessary for such systems. ITER or DONES are the same. And of course, we apply parallelization MPI or OpenMP. So we evaluated speed up. It's almost linear, you see, with a low number of processors, of course. So we cannot we cannot deploy for many thousands. Just for 1,000 it works good, but after that it comes to the saturation to the plateau because we have a lot of cross communications between tracks. So that's the reason. So
yeah, very nice. Yeah, no, but
you can check articles I provided here, and for Mac Delicious development I also put some references. So
thank you. Thank you very much. So
my pleasure.
I think we have a question here. Did you study the tritium production?
Yes, of course. Yes, of course. We studied lithium production in lithium, and we calculated all particles, secondary particles produced by deuterons. So we calculated alpha particles as well, because it's a question of thermal expansion. If you have some material like urethane, and alpha particles can produce like bulbs and cause problems with welding, revealability problem in urethane if you have alpha production. Yes.
Thank you. Thank you very much for your talk, and we will move on to the next speaker. So the next speaker is Dominguez-Gutierrez from the National Center for Nuclear Research in Poland. So if
hello.
Yeah, so if you can share your presentation.
Can you see my screen?
Yes.
And now it's full? The full
No, well, maybe now. Now it's full. Yes.
Okay.
All right. Okay, so you have 20 minutes and including questions.
And questions, okay. So, hello everybody. Thank you so much for this opportunity. And I would like to thank the organizers for giving us this opportunity to present our work here in the 5th event. That is really nice that we can have the 5th edition of this high performance computer fusion meeting online. This talk, I'm going to present this talk in collaboration with my colleague from the National Center for Nuclear Research, Timothy Kavan, who will present the multiscale modeling in finite element methods. So in order to test the new materials that we need to replace the current components for nuclear plants, nuclear applications, fusion, reactors, all of these things, we need novel materials with promising mechanical properties. How can we know and say that these materials have good properties and are the promising materials that will be replaced because the current materials and components are already at their limits? One method to test if these materials have such promising properties is nanoindentation. The concept of nanoindentation mechanical test is straightforward. You have an indenter, penetrate the material, and you measure, according to the theory of Oliver Farr, the loading as a function of the displacement. Then you calculate with some fitting the hardness of the material. The concept, as I said, is quite straightforward to understand. We have an nanoindenter in our lab. We can do experiments, and also we can do modeling. When you have this collaboration, close collaboration between experimentalists and people doing modeling, is straightforward to analyze what is happening in the experiments and to more or less support the experimental work by multiscale modeling. For example, in this graph, our expert in an indentation in NCBJ, Katarzyna Mulewska, obtained this lot as a function of the indenter tip with a spherical indenter, and we can characterize the LD curve and the process of nanoindentation. The elastic part, which is characterized by the Hertz fitting, Then the transition to the plastic deformation region, which is identified by the pop-in the experiments and in the computational modeling by molecular dynamic simulations, obtaining a reduced Young modulus of roughly 200 GPAs for the experiment and for the modeling. Here I can show how a large-scale molecular dynamic simulation looks like for iron. We have 25 million atoms with this size, which is still for this scale and into the limitations, time and length scale of molecular dynamic simulations. We can learn what are the mechanisms when you load, when you are doing the indentation load and when you remove the indenter tip. Not only for pristine materials like here in iron, but also for other alloys with this material, 9% of chromium, that you put, as we do in modeling, randomly allocated chromium atoms, and then you can study what is the effect of chromium in the propagation, in the nucleation and evolution of the dislocations, and also the nucleation of some dislocation loops that are observed in nanoindentation, in indented samples. These samples, as you can see here, all the analyses that you can observe during the whole process of nanoindentation for the dislocation structure, the dislocation network underneath the indenter tip, and all of these dislocations can be observed by DEM images by experimental group. And here, when I'm saying that the slip traces and the pileups can be compared to SEM images by the experimental group. This sample is the 111 direction for iron, which is my favorite crystal orientation, to explain how the lasso process is modeled by molecular dynamic simulation. And you can see that this edge dislocation will nucleate a loop, as you can see the comparison one-to-one between the pristine iron and the chromium alloy. We can learn how all of these simulations are being done. And as I said before, we also can compute the geometrically necessary dislocation density that can be obtained by it first in the indented sample. In the experiments, as you can see here in this image at your left side, is the EBSD image with the indented sample. You compute the GND's density also from the experiments, and then you perform, by this guidance, you perform molecular dynamic simulations to obtain similar shapes for the GNDs when you compare to the experimental work. From MD simulations, you also can provide information to upper scale, which is discrete dislocation dynamics. And this data that can be used in the DDD simulations can be more close to the experimental data, to the experimental images and results. And all of this can be characterized and compared in a qualitative way to the experiments and also for the molecular dynamic simulations by using stress-strain curves, because all of the experimentalists more or less are used to see stress-strain curves from tensile or compression simulations. After you characterize everything for the pristine case, it could be interesting to see what is the effect of irradiation in the sample. What happened with the dislocation evolution, what happened with the dislocation nucleation, what is the effect, the hardness, why the material increase the hardness, what is the hardening process. For example, for this irradiated pure iron sample, we notice that for the pristine case, you have this evolution in the 0-1-1 orientation, the evolution of these half loops in the corresponding strains, according to the crystallographic nature of the sample. You nucleate the loops, but when you have an irradiated sample, you already have the sample with predefined loops. And this decoration of the sample with all of these vacancies, voids, dislocation loops with Borger vectors 111, and also the junctions, all of this will affect the behavior and evolution of the fresh dislocations that are coming from the indentation part, from when you are penetrating the sample. These fresh dislocations are the ones that are being nucleated because of the pressure from the indenter tip in the sample. They are going to capture the already formed dislocations that were nucleated during irradiation. And when you remove the indenter tip, this will absorb and try to clean all of these dislocations from the sample. This is the case of our experimental group that they observed before doing the nanoindentation. They have a dislocation density which is bigger than the one that they have after nanoindentation, and this can serve as a guidance to the experimental group. Now I pass the microphone to Timothy. Timothy, please, your turn to explain
Yes.
finite element method.
Good afternoon, everyone. I hope you can hear me now. So yeah, I will present the experimental part, experimentally finite element part of this work. I work in parallel group with Javier, and I extend the scale to a higher level. So I just want to add something to the background, which was nicely explained by Javier. So why do we need to irradiate materials with ions overall? It's just because we try to imitate the neutron damage to analyze the materials and their performance under the neutron flow in the reactor operational conditions. And on this slide, you can see the summary of my last couple of years work. I was developing a finite element, crystal plasticity finite element method model to simulate the nanoindentation process in iron, starting in iron. On top, all the results are coming to pure iron. And you can see that it was possible to closely reproduce, for instance, experimental force displacement curves, hardness values, also dislocation density evolution. Then we introduced a nice approach to correlate the scales of deformation by overlapping the FEM maps with TM lamellas, FIP extracted lamellas observed with TM, and also the patterns of indentation pileups. All this indicates that model predictivity is quite high, so we can basically interconnect the experiment and simulation using FEM. And this all is needed because if you look on the bottom of the slide, which is now the results of Eurofair, we perform everything the same for the reference Eurofair. And then the approach I introduced during my PhD is to imitate the ion radiation as a subsurface layer, subsurface layer, which split into smaller layers. And we have the damage depth profile, irradiation damage depth profile, which is coming from stream software, for instance. And we average a dose, for each layer according to stream profile. And then we introduce a new material law based on the reference one. We introduce it to each layer, and we can then simulate and obtain the hardness levels from experiments and simulations. And once we have a good replication of this ion radiation results, we can then transfer these material laws into simulations of macro scale deformation, like tensile test, for instance. And it will give us a tensile curves which are representative for at least yield stresses. We focus on yield stresses here. They are representative to a neutron radiated material. So basically we used just one ion radiated specimen, crystal plasticity FEM approach, and obtained yield stresses of neutron radiated material without using the neutron radiation, which eventually saves a lot of time, costs, of course, and so on. Please, next slide. So I have a lot of ideas how to extend these results and how to extend this model. And one of the approaches is to try it with another indenters. So using the data we have from our experimental group, which were presented before, I started to imitate, before the data was done for Berkovich indenter, and I tried to do it with a spherical one. And you can see the FEM setup on the left, how it looks like. And on the right, you see the main constitutive formulation, which is used to calculate the plasticity in this method. And you can see that it's classical for crystal plasticity to calculate slip rate, but then we also look for slip enthalpy or probability, and this is also coming from molecular dynamic simulations. And also we have dislocation interaction strengths, which is coming from molecular dynamic simulations. So basically, we can interconnect the work of Javier to extract some parameters which are needed for my simulations. Then there is also dislocation density evolution, which is important because we can predict and compare it with results obtained like from TM, which I will show later. Next slide, please. So what do we do exactly is we use experimental tensile tests made on reference material, non-irradiated, and then we use this constitutional formulation and crystal plasticity FEM to fit. Some parameters are fit, some parameters are taken from literature. Go back, yeah. And we obtain the set of we obtain the constitutive laws in a set of temperatures, which allow us to replicate the constitutive law of material. And then we introduce this, once it fit, we introduce this material law into the simulations of nanoindentation, which to the setup I showed before. Next slide, please. And this allows us to obtain the force displacement curve with a good accuracy. Here it's just 200 nanometers depth. I don't really like to work on this depth because we need to consider the size effect, but overall, yeah, it's possible, and it's better to go on the higher depth. And yeah, then we can analyze the FEM outputs. Next slide, please. And compare them with experimental results. And here you can compare. So on the right, you can see some TM done on the similar indentation, but in reality. And then TM was used to obtain the dislocation density. And on the left, you can see the FEM map produced by my model. And by the dashed square, I kind of represented the TM part, which is taken for observation, and you can see that the dislocation density was predicted like with the accuracy of around 11%, which is, for my opinion, extremely good. And considering that also dislocation density is usually calculated in power of 10, so we can be sure that this model predicts gives nice results comparable to experiments, that they are realistic. And then the next step is to basically introduce some radiation effect, as I showed before, with the layers, and try to extract, try to find it first to correlate with ion radiated material tested with nanoindentation, and to recover some, like say, representative material laws for neutron radiated material. Yeah, that's it. Next slide. This is a thank you slide.
We would like to thank you. And here I'm leaving only the visualization of we can call it one of our success in our lab, which is a machine learned large scale molecular dynamic simulation of a tungsten tantalum alloy. This is tungsten 70% and tantalum 30%, which is one of our very large MD simulation with more than 50 million atoms, and try to provide as much information as we can for the largest, the multi-scale modeling. And I would like to thank everybody for this. Thank you, Timothy, for helping.
Thank you, Javier. Thank you, everyone.
Thank you very much for the very nice presentation. So we have some questions in the chat. So the question is if which CP-FEM code are you using, and for which FEA solver?
Yeah, so FEA solver, it was developed in the University of Liège. It's where I developed in Belgium. It's where I made my PhD. It's not available on GitHub, but it's available on GitLab. It's possible to use it under some free license, but I'm not sure if you need to get an invitation for using it from the developer of the professor who developed it. But it's even if yes, it's very straightforward. You just contact him via email. I can provide it to you, and you explain who are you and what you're doing, and he will be happy to share. This happened with me several times already. I introduced it to other people. For crystal plasticity subroutine, it was developed also in Belgium, but in another university, in Louvain-la-Neuve, by another professor. So these two things are interconnected with the UMAT interface. So it's also possible. This is the framework, basically.
Thank you. Okay, I don't see any hands up. I have a question about the molecular dynamics, these very nice simulations that you have here. I do molecular dynamics simulations myself, and always the question is that the rate in the simulations. Do you think that plays a role compared to the rates at which you actually do the nanoindentation in the experiment?
Yes, it does. We have been analyzing the loading rate. And yeah, we noticed that this is important parameter. And in molecular dynamic simulations, the lowest rate that we can go is 10 meters per second, which is a little bit too much high for experiments, but into this scale and high stresses that molecular dynamics is based on, 10 meters per second is the correct loading rate for this kind of simulations, and to see the propagation and nucleation of the dislocations. So yes, it does, but it is into the parameters that can be evaluated for the experiment.
Thank you. Thank you very much for
something that I would like to comment, that is not only the rate, and we have been observing in MD simulations, is that these simulations of nanoindentation are open boundary simulations. So if the interatomic potentials don't have enough information for the surface, the stacking fault energy, the beginning for the modeling of the elastic part of nanoindentation is modeled like a toy model, is incipient, is like nothing correct, and the potentials are only modeling the nucleation of defects after crossing the pop-in of the yield point. So we have investigated too many potentials, and we noticed that the interaction of the indenter with the top layers of the atomic layers of the sample, this elastic part is modeled like artificially if you are only pushing the atoms artificially. So the interatomic potential need to have enough surface information and also for the stacking faults.
Yeah, which is sometimes it's true. It's not taken care of because we think of the bulk properties.
Yeah,
that's
exactly.
True. Yeah, very nice. So thank you, and we move on to the sorry. So we'll move on to the last presenter this afternoon for this session, which is Pablo Canca from the University of Granada. So, Pablo, if you can share your presentation. Pablo, we don't hear you. I don't know if you're talking or, but we don't. Pablo, are you there? I see you're here and that you are, let me see. And your mic is on, but I don't hear you.
now?
Oh, now.
Okay,
Now.
I'm sorry.
Yes,
Yeah,
good.
there was
Okay,
there was an issue with the computer. I also have an issue with the camera, so I won't be able to.
that's fine. Can you
Yeah,
share the
I have shared
presentation?
the screen. Yeah,
Good.
there we go. Can you see it now? But
Yes.
the wrong one. No, you can see it, right?
Now it's fine.
Okay,
Yes.
great.
Thank you.
Okay, thank you. Good afternoon, everyone. Thank you for allowing me to talk in this workshop. Thank you, Maria Jose. My name is Pablo Canca. I'm a PhD student at the University of Granada, and I'm going to talk to you about one of the main aspects of my thesis, which is the ab initio study of cementite ferrite interfaces under irradiation. I'd also like to thank my collaborators, Dr. Chuchun Fu from COA, Dr. Christophe Ortiz from CMAT, and Dr. Blanca Biel from the University of Granada. So first of all, when talking about irradiation damage characterization, we first need to have a good understanding of the system that we're going to try to simulate, usually with object kinetic Monte Carlo methods, for example, but all that first needs a prior understanding of the system. And in this case, it's a cementite ferrite system that I will describe later. We know that carbon complexes in steel have a significant effect on its structure evolution under irradiation. But still, there are many mechanisms that explain the arrangement of carbon in ferrite that are not well understood. So trying to simulate defect evolution in these systems that contain carbide is sometimes challenging due to the lack of understanding of the systems. And so we want to use simulations that go, so DFT and molecular dynamics to try to better understand them. The system contains cementite, which is a carbide that is naturally produced in steels because austenite has a higher saturation point of carbon atoms than ferrite. And so after cooling austenite, some carbon saturates in the lattice, in the ferrite lattice, and some of these solids arrange in the form of cementite. Even the process itself of cementite nucleation is still not very well understood, but we know that it is expected to appear in some of the materials that are going to be used in fusion. So we want to try to better understand cementite to predict how the irradiation damage will affect precisely the interface between cementite and ferrite. So when we want to model interfaces, we first, of course, need to pick an orientation relationship because there could be an infinite amount. And the one that we have chosen is the Bagariansky orientation relationship, which is the one that has been studied the most in the literature. But despite, which looks like this, but despite having been the one studied the most, there are many discrepancies in the literature as to which is the most stable orientation or what is the interface energy of the Bagariansky orientation relationship or what happens when we add defects to it. And we also know that the likelihood of any interface to appear is going to be related to its interface energy. So that's going to be the main magnitude that we're going to be working with to know whether an interface is likely to appear in nature or not, interface energy. And also at the same time, we're not just going to take the Bagariansky orientation, so the interface plane that I showed you before, but we're going to imagine that our cementite forms a cube with the Bagariansky orientation, but that produces three different interface planes, not just this plane here, but also this one and this one. So in total, we have three interface planes that we want to study. And at the same time, an aspect that is usually overlooked when discussing cementite interfaces in the literature, which is the influence of the terminating layer. So we're also going to study not only the three interface planes, but the 6 termination layers that we find for this orientation, the 3 that we find for this one, and the 4 that we find for this one. So that in total amounts for 13 interfaces. So we now have to build them, but building interfaces using simulations is usually tricky because we have a mismatch, and because of periodic boundary conditions, you cannot just leave a gap in your system. You have to close the gap, and you have to do that by adding an artificial strain to your structure. This orientation presents a mismatch that is high enough as to be considered, let's say, problematic. And so instead of just having one unit cell of ferrite and one unit cell of cementite, what we're going to have is to find common multiples of the lattice constants of both materials so that we minimize strain. And we can do that, and we can heavily reduce strain in the system at the cost of increasing the number of atoms dramatically. And so when we see this number of atoms, although for the colleagues that do molecular dynamics, this is probably not such a shocking number, but for us who do mostly DFT, it's quite a big number. We have to decide which technique should we use. And this is, of course, a typical multiscale problem. And we have to discuss how big is my system, what timescales am I interested in, and also, very importantly, do I have reliable potentials to study my system using less accurate, more efficient methods? Which would be the case for molecular dynamics. That is precisely the range that would be ideal for our system. The problem is that the potentials that are found in the literature are not trained for these interfaces. They're just trained for cementite. And so we cannot be sure if these potentials are going to accurately describe the system. So instead of doing this, we're going to try to find a detour so that we can use DFT and molecular dynamics at the same time while verifying if the molecular dynamics results are valid or not. And we're going to do that by first building these very big interfaces with very low strain using molecular dynamics, which will give us some results. Then we will study small interface with high strain, also using molecular dynamics, and this will allow us to study the effect of strain in this system using the same technique and the same potentials. And finally, once we know this influence, we will study these same small interfaces using density functional theory, which only allows us to work with systems of a few hundred atoms. So taking this detour, we start, as I said, using molecular dynamics for big systems. We chose an MEMA potential by Liénage. And also, you could say we're not going to do molecular dynamics, but molecular statics, since we use the conjugate grading algorithm and we only minimize the atomic positions. This is because these results, the goal is that they lead to, they give us results that can be studied with density functional theory as well. So we keep it at molecular statics so that the result can be compared. And these are the results that we find for the 13 interfaces that I mentioned before. And out of these, we find 6 interface energies that are low enough as to be of interest to us. So we expect them to be prominent in nature. And actually, these 2 orientations are found in the experimental literature. And now we move on to DFT. How can we do that? First, we study the influence of strain, as I said. And here what we have is a graph of the effect of strain in one axis parallel to the interface, and the other axis parallel to the interface. And the color represents the shift between the result that we obtained at first without strain, with very, very low strain, and the result obtained now with high strain. And what we find is that if we stick ourselves to this region here of strains of less than 3%, then the effects that strain does on our interface energy are not so dramatic. And at the same time, we have to study the influence of the relative position, because not every relative position between the cementite structure and the ferrite structure is going to predict the same results. And so what we do is shift the positions of cementite with respect to iron, with ferrite, sorry, and we obtain these graphs of high and low energy values, which can be linked to symmetry positions. The high energy, for the example that I'm showing you right now, predicts that the high energy peaks are found for ferrite cementite interfaces where both iron atoms are on top of each other, whereas the low energy cases happen when we reproduce the structure of cementite, this zigzagging structure of cementite. So when we move on to DFT, we're also going to try to reproduce this same structure so that we know that we are near the least energetic position. There's required 32,500 simulations. So of course, trying to do this using density functional theory directly would have been impossible. So this information is very valuable to save time and computational resources. And these are the results that we obtained. Here we have the molecular dynamics results for high strain interfaces, and here between brackets we have the results for low strain. So as we can see, the 010, this interface 010 parallel to the 112 ferrite interface plane. The molecular dynamics, the effect of strain is near 0.1 joules per square meter. But for the case of the 001 interface plane, this one, we find that the difference is much higher. So of course, this means that the effect of strain is high, but it's the best that we can do if we want to study this interface using density functional theory. So we take this as a reference of how much our values are going to change when doing DFT due to strain. And here we find the results using density functional theory, using the GGA PB and these values of for energies and forces. And we find that these results here, which are quite similar, although not exactly the same, they also deviate to the results obtained from molecular dynamics. So the result that we obtained is that these potentials were trained good enough to predict the interface energy of these interfaces. To verify and better understand our results, we implement a bond order broken and new bonds method, in which we study the surface and interface energy of the structures that we studied by means of the number of broken and new bonds, and by means of one order, which is proportional to bond strength. And what we have here is a magnitude called omega, which is basically a weighted summation of the number of broken bonds for the case of surfaces, because surfaces, of course, don't have any new bonds. It's they only have broken bonds. And in the y-axis, we represent the surface energy, and we find a very good correlation. This means that this model is predictive. If one wants to better understand, to try to predict the surface energy that a cementite surface will have without needing to needing to compute the surface energy directly, they would be able to do so by using this method of this broken bond method. For interfaces, however, it's a bit trickier because we also have to take into account the influence of new bonds, which is taken here in this term, and at the same time, because of strain and because the interfaces that we have studied have strain, we find that the interface energies don't correlate with each other between different orientations, and we have deduced that this is due to the effect of strain. However, it's still a predictive method that shows us a correlation between the number of broken and new bonds and the interface energy. So here you have a summary of the results that we obtained. And as I said, this interface is the one that presents the lowest interface energy predicted by all methods, high strain, low strain, the DFT, and molecular dynamics. Lamps potentials, we found out that they are a good approximation to DFT, although we find differences. And we also found a way to use DFT without exploiting too many computational resources. And at the same time, we can predict the MD results with a bit of better accuracy at the cost of also increasing strain. And the next step, which I'm doing as of now, I've been doing for a few months, is study how the addition of defects to the interface influences the stability of the interface. And here we prove that we actually needed to take this detour because the existing molecular dynamics potentials do not predict the interface, the deformation energy of defects in general in the interface. So we need density functional theory. This, of course, has the goal of finally implementing object-kinetic Monte Carlo simulations and also predicting the irradiation damage evolution. And we're also just starting with my colleague, Pedro Delgado. We just started training the potentials using machine learning, DFT training potentials, which is also expected to heavily increase our computational capabilities and to study these interfaces without strain using much better potentials than the ones that are already existing. So thank you very much. Do you have any questions?
Thank you very much, Pablo. So if you have questions, please post them in the chat or raise your hand. So Pablo, I have a general question. One of the difficulties here in the simulations is your starting point. So there are so many different configurations that you can choose from and that you have to check. So I was wondering, do you think all these new algorithms of artificial intelligence could help in this?
Yes. Maybe I shouldn't say it, but what took me a year of DFT, a heavy computational times, molecular dynamics, trying to compare the results. What my colleague Pedro has achieved using machine learning results, everything I did can be solved much quicker, much quicker. Especially because it's easier to compare with DFT results and it's easier to trust the results in the way we're training the potentials. And so all these calculations can be done much quicker.
But for that, you need a huge database to start with from DFT. Is that correct?
Yes, exactly. And to train this system, we're using all the work that I did last year, and we're using it to train the potential. So it's good that these calculations are already done. The good thing is that these potentials have an extrapolating capability. So these potentials, Pedro trained them to with cementite and interface results, but they are able to predict defects in the interface. And they work quite well with the results that I have for defects using DFT.
Okay, so we have a couple of questions in the chat. One says, what kind of problems do you face during the formation of the interface of cementite?
During the formation, as in building the interface for the simulation, or the formation like as a natural process?
I think
like
it's
the section,
I think
right?
that in the building the initial configuration is my guess.
So the first thing that okay, so mostly it's strain related. You have to find a compromise between how much computational power you have, and which will decide how many atoms you can work with. That is, of course, one issue. And then trying to deduce the most stable relative position is also quite tricky. It also trying to compute the bulk energies for non-stoichiometric cementite structures presents many problems. So the possibilities are pretty much endless to what you want to do to the interface. The problem is that we don't have an endless amount of computational resources.
And another question from the chat is, how large do you think your database of DFT-based results could have to be to represent a reliable training set to improve your interatomic potentials? And also, what is the methodology that you use? GAP or SNAP or?
So we're, as I said, Pedro is the expert in training the potentials. I'm just starting to catch up with him. But we're training these DFT potentials for machine learning. these machine learning potentials using Maze, which was developed by the Cambridge University, and the data set is quite big. It's quite big. I don't want to give you a number. I think Pedro is in the chat, so maybe if he wants to give a number. But yeah, we're using Maze. We tried Snap as well, but we switched to Maze.
Okay, thank you very much. I think for the sake of time, because we already are running over our time slot, we should thank all the speakers, and we will reconvene at 3:30. At 3:30, we start with an invited talk. So we'll see you back at 3:15. Thank you. Thank you very much. 3:30, sorry. Thank you very much to all the speakers today.
Okay, so maybe we can start with this very interesting session that is my pleasure to chair. I am Dr. Iole Palermo from CMAT. And today in this session that is called Systems and Multiphysics, we will have 3 presentations, each one of 20 minutes, including questions. So after the speaker, after the presentation, you can both write inside the chat and I will read the questions, or you can raise your hand and present the question. So maybe we can start with Dr. William Ellis and his talk about the virtual fusion tokamak structural model enabled by supercomputing. So please.
Okay, can you see my slides okay?
Yes, it's okay.
Okay, wonderful. So yeah, I'm William Ellis, sadly not a doctor, but I wish I was. And I'm working currently at UKAEA, and this presentation will talk about some work that we did generating a virtual tokamak model for solid mechanics modeling. So let's get started. So it's pretty common practice in engineering departments to use numerical models to determine stress and strain fields in individual components. You can use knowledge of those stress and strain values to help unearth interesting characteristics in your component design. And you might use knowledge of those characteristics to help avoid potential failure mechanisms, or to optimize for component lifetime, or to reduce the use of expensive materials. The figure on the right shows a hypervapotron as an example of an individual component, which is just a fancy name for a heat exchanger, really. And you could do thermomechanical analysis on this geometry, throw some relevant boundary conditions on their model thermal expansion, and you could pinpoint areas of potential interest, maybe areas of significant stress. But individual component analysis has some shortcomings. Firstly, we rely on boundary conditions to define the operating conditions in the environment external to the single component model. And potentially we miss behaviors which are only emergent when you have a more holistic view of the entire device. So I think knowing that, it's important to try and look at what's stopping us from scaling up from a singular component to more integrated models, for example, an entire reactor. So HPC resource, that's not the thing stopping us. We have access to the necessary hardware. You might argue that the individual engineer at their desktop computer doesn't, but let's assume HPC access, given we're at Fusion HPC. And access to scalable numerical analysis tools is also not a blocker. There are plenty of highly parallel codes out there that can utilize the HPC hardware we have available to us. But the availability of simulation-ready large-scale CAD can be a blocker. Making suitable models is time-consuming and not easily automatable. So that's what we're going to try and do. Now we're going to try and prepare a full-scale model of a tokamak for mechanical analysis, namely Mast Upgrade, one of the reactors we have on site at UKAEA. And you might be asking, don't you just have well-maintained CAD of your reactors? And fortunately, we do, as we should do. But CAD can have different intended use cases. Sometimes CAD is to be sent over to manufacturers for actually getting your components made, and henceforth is extremely detailed. And sometimes CAD is for visualization purposes, for using in presentations like this one. And if you're really, really lucky, CAD is actually prepared with the intent of meshing it and using it for analysis. And the high fidelity CAD of MasterU that we have available to us is not analysis ready. It's extremely detailed. It's riddled with overlapping geometry, and it's not really meshable into anything coherent. So you may then be asking what actually makes CAD analysis ready. And I would argue that analysis ready CAD is detailed, but not too detailed. And you might be thinking, I just told you that HPC enables large scale simulations. And it does, but resources aren't infinite. If we were to mesh the highest fidelity CAD we have of MasterU with all the screws and washers in a fusion reactor, we could end up with a mesh of billions of elements, which on its own, you might be able to make that mesh. But if you actually want to then model the physical interactions between all those small connecting nuts and bolts, which given you've modeled them, you may well want to do, suddenly your problem is unwieldy at best and just impossible to solve at worst. So yeah, things get a bit insane if you model down to the individual bolt. So even though HPC does enable large-scale simulations, there are still limits. Analysis-ready CAD should also be suitably imprinted and merged in order for the resulting mesh to make any sense. And if imprinting and merging doesn't mean anything to you, don't worry, because I'm about to explain it a little bit. Analysis-ready CAD should also be tractable by meshing software. And by that, I mean, you can't have some gross self-intersecting geometry that's crossed 6 different CAD applications and file formats and is fundamentally broken. That won't work. I wouldn't call that analysis-ready. And for use in Monte Carlo particle transport codes, you can't have any volume overlaps because you don't want to lose particles when you're doing those simulations. So what's that imprinting and merging thing that I was talking about? So as discussed, you can't simulate every screw and bolt and piece of gum and blue tack in a fusion reactor. That's currently a no-go. It would require a crazy amount of fidelity. So we have to make some simplifying assumptions. In this model that we're making, we approximate physical connections between components by effectively gluing coplanar surfaces together. And to do this, we have to make sure that the mesh of our reactor is conformal across component boundaries so that field values are continuous across different pieces of the CAD. And we achieve a conformal mesh by forcing components to have like topology. In other words, similar surfaces that we can merge together into one to force the mesh to be conformal. And this practice is called imprinting and merging, and we use Coreform Qubit to do this. And I have a visual example, which personally I find more helpful. So here's 2 cuboids stacked on top of each other. They're currently not imprinted, they share no topology, and then when you mesh these two, what you get at the interface is this horrible, non-conforming, overlapping triangles mess. And field values won't be continuous across these 2 cuboids. And mechanically, that manifests itself as the volumes providing no support to each other. They're not glued together, essentially. But if you imprint, suddenly the curves from the smaller cuboid are present on the large cuboid. And if you then mesh this, now that they have shared topology that I was talking about, they've got a similar surface that you can merge together. Suddenly, at your interface, you've got a lovely conformal mesh, and field values will be continuous across this. They provide support to each other now. Unfortunately, it's not completely this easy. Once you start imprinting large CAD assemblies with lots of curved surfaces, you have to start worrying about tolerances, and it gets painful. But this should at least provide some intuition as to why we need to do this. So how do we get to our usable CAD of our Tokamak that we can imprint and merge and eventually mesh? We could either go top down, we could defeature from a super high fidelity model, or we could upfeature from a low fidelity model. And we're going to go with option B, given that manually defeaturing would be extremely time consuming. And at the end of manually defeaturing, there's no guarantee that we're left with any geometry that makes a lot of sense, that's non-overlapping and actually meshable. So we're going to go option B. We're going to up feature lower fidelity CAD. And our lower fidelity CAD that we've started with is a model of mass tube previously used for neutronics analysis. This is a good starting point for us, as we'd eventually like to run neutronics analysis on our full-scale model. And if we want to end up with no overlaps, we should at least start with none. Unfortunately, in this model, there's a lot of mechanical support missing. There's lots of pieces of geometry here that are just floating in midair, mainly because gravity was not necessary for these initial neutronic simulations that this model was used for. Whoever was using it only really cared about the neutron deposition on the first wall components. So we're going to have to implement all the missing mechanical parts to actually provide support to these floating components so that when we apply gravity, these things don't fall into oblivion. And instead of showing you each individual part we've added, I've just kind of got a couple of the main pieces here. So here's what I made earlier. These are most of the things that we added. There are lots of other small components, but it's not worth going into it, really, I don't think. And if you look at before and after visually, there's quite a clear difference. The model actually has legs now, which is good. It's being supported. There are magnets. And if you look at the mass before and after of the neutronics model and this new model, we get a lot closer to the total mass or to the real mass of the real reactor. And actually, with this CAD, once you've imprinted and merged everything, you get about 8,000 imprinted and merged surfaces. So there's 8,000 points of connection in here between individual components. But now that we've got a piece of CAD which makes sense, we have to mesh it. But to mesh it, we need to know what kind of mesh resolution we need to use. And to determine the necessary mesh resolution, we did a quick mesh conversion study. We used a simplified version of the geometry for this, which was made up of essentially the vacuum vessel, the legs, and the central column to avoid super long run times for this convergence study. And we ran our gravity simulations, so just a linear elasticity model, looking at the stresses resulting from the vessel's own weight. And we ran this gravity sim on an increasingly globally refined version of the simple geometry. We reduced the global mesh sizing everywhere until we saw convergence of our von Mises stress in these gravity simulations, because this gave us confidence that we're fully resolving the maximum stresses. Then, using the most globally refined version of this testing geometry, we could locate the areas of really high von Mises stress, and then go back to our model. And instead of globally refining the entire mesh, we could just locally refine those regions of very high stress to produce a mesh which more efficiently uses the nodes in the mesh, which are effectively the degrees of freedom in your finite element solve. So we're reducing some computational burden there, which should manifest as waiting less time in HPC queues, which is good because no one likes waiting for compute. So after determining necessary mesh resolution, we generated the final mesh using Core-Form Qubit again. So there's about 4,000 individual parts here meshed into 127 finite elements, only first order tetrahedra right now. We have played with second order, but for, again, not waiting in extremely long HPC queues, we chose first order now. Preliminary neutronics results show no lost particles in this mesh. So there's no volume overlaps, which is brilliant. This gives us good confidence going on to physics past solid mechanics. If we want to run any particle transport codes, then this should suffice. And there are three materials being modeled here. We've just got steel, copper, and graphite. Copper for the magnets, steel for most of the structure, and graphite makes up the majority of the first wall components. And to appease or to, I guess, give some respite to anyone who's worrying about the actual quality of this mesh, or to help relax them, we did some mesh quality analysis. And so looking at the aspect ratio, which is effectively the longest side of a tetrahedra over the shortest side, you can use other formulas to calculate your aspect ratio, but that's basically what it is. We see that the large majority of our elements are within a reasonable aspect ratio. There are one or two which have a horrible aspect ratio, super elongated elements, but out of 127 million, this is okay. And we use another metric, which Qubit refers to as the shape metric, which where one essentially is a perfect tetrahedra. A shape metric of 1 is exactly what you want, and anything below 0.2 is pretty horrible. And we see that, again, almost 100% of our elements above that 0.2 value. So we have some confidence in the quality of the mesh. Our simulation tool of choice is the MOOS finite element framework. It's a C++ based finite element framework that comes bundled with numerous different physics modules, which are pre-validated, which is brilliant for us. We don't have to do any implementation of physics, so that saves us some time. And it's really highly scalable code. It's been shown to scale up to 32,000 cores, perfect for large-scale sims running on HPC hardware. So now we've got a model, we know what software we want to use to run our simulations. Let's run something. So the first full-scale simulations we did modeled the reactor subject to gravity. So any displacements here are resulting purely from the vessel deforming under its own weight. Again, it's a linear elastic model. We're assuming small deformations to use a linearized strain tensor. And we have Dirichlet boundary conditions fixing the displacement at the bottom of the 4 legs to 0. So that's our boundary condition here. The results from the simulation show maximum displacements in the region of about 1 millimeter on the top and bottom end plates of the vessel. It would be nice, given that we have this reactor on site, to have some great real-world data to compare to, but unfortunately we don't. Given the reactor is covered in shielding, it's hard to get to and go and measure. But estimates from people who actually work at MassU put the maximum deflections within about 2-3 millimeters. So we're on the right order of magnitude, if maybe a little under in this case. And if we look on the HPC side of things, we used 14 Sapphire Rapids nodes to run the simulation, 336 MPI tasks, 12 MPI tasks per socket. This is a very memory bandwidth bound problem, so we didn't use all of the cores on every node. Ideally, we would have 8 MPI tasks per socket, given Sapphire Rapids has 8 memory channels, but you also splitting the problem into smaller chunks makes it run a bit quicker as well. So the solve time for this was about 55 minutes, almost an hour, which you can start to reduce if you mess around with preconditioners and try and optimize your linear solve, or just have more compute available to you. We also looked at the impact of the pressure differential, which would be present in operating conditions, so vacuum conditions inside the vacuum vessel, as the name suggests, and atmospheric pressure of 1 bar on the outside. And for this simulation, the boundary conditions are, again, well, fixed displacement on the bottom of the 4 legs, and then atmospheric pressure of 1 bar is applied to every external surface of the tokamak. And then we fix the pressure in the vacuum vessel on every internal surface to 0. And we can see the resulting stresses. Here, the displacements in the pictures are magnified to show off that it actually does displace. Don't worry. Air is not destroying our tokamaks, fortunately. And we can actually compare the stress results from the gravity and the vacuum condition simulations. Here we have a metric called the density of stress, which is effectively like a probability density for the stress values in the finite elements in the mesh. And we can see that the graph kind of demonstrates that the elements are under relatively low stress, or at least the majority of the elements are, but the tails of the distributions indicate that there's a subset of the elements under significant stress, which is sensible. There's going to be areas of the model under high stress, given the weight of it. Interestingly, the stresses from the atmospheric pressure are higher than from gravity, which is just fun to point out and to look at. And then finally, or the final simulation that we ran using this model, looked at frequency domain analysis. So in a real fusion reactor, you could have abrupt termination or of your plasma, or instabilities in your plasma, or time-dependent electromagnetic forces, which can kind of give rise to oscillatory motion. But we can't model disrupted plasma currently, but we're still interested in kind of looking at the oscillatory motion of the tokamak. So we basically solved the 1D wave equation on the model, and we could get out the resulting frequency analysis. So we could see which components were resonant under different conditions. I should mention that in this problem, the boundary conditions are not fixed displacement at the bottom of the forelegs. We're actually applying oscillatory motion on the bottom of the forelegs. So that's why sometimes these two lines line up in that the rest of the vessel is moving with the legs, and then these spikes are where you get resonance in different components. And
William,
we've got sorry.
Can go faster, please, because you're a little bit late.
Yes, sorry. I've got one slide left. So the takeaways from this, CAD is a big blocker. Model preparation took up the majority of the time required to actually do all of this work. And the HPC resource and software capability is there. So, CAD is the main problem here, and getting models out for large-scale sims is difficult. Whether we actually go from here, these results are unlikely to impact any actual design decisions from our STU, but now that we have the model, we want to use it to show off our kind of multi-physics framework. So we can dive into other physics like neutronics. We might be able to feed irradiation-induced material damage back into our solid mechanics simulations, which would be interesting. We'd like to do some electromagnetic sims and some transient simulations, seeing as all the ones we've done so far are steady state. And that's me done.
Okay, thank you so much. So I have seen a question in the chat from Sheraz Khan, who asked, why is meshing important in simulations? What is the smallest mesh size that can be used in simulations? And what is the relation between the meshing size and quality of simulations?
So with regards to why the mesh is important in simulations, so your mesh effectively determines like the resolution you can get out of your results. So on what sizing you can use, that's kind of completely dependent on your geometry. If you've got a larger problem, you can afford to use, or at least your geometry is larger, you can afford to use a larger mesh sizing and still capture roughly the behavior in that model. Yeah, so it's very dependent on the problem that you have.
Okay, I understand. There is another question by Jae-Min Kwon, please.
Thank you for very interesting talk. So you plan to expand your modeling capability include electromagnetics, it looks like. And I'd like to ask your opinion about these required mesh properties regarding this electromagnetic simulation, which do you think similar kind of quality mesh for structural analysis would be enough for this electromagnetism, or would require a bit different properties?
That's a good question. So I think for initial electromagnetic simulations, we would rip the same magnet models out from the solid mechanics mesh and try and do some closed coil solves on those. They are very rough models, they're effectively they're just solid blocks of copper. They don't model the actual coils in the real magnets. So initially, we would use the same mesh, yes, but I think in future, as our kind of capability increases, we would inject higher fidelity models of the magnets found in MAST into this mesh to kind of better resolve the electromagnetic fields and kind of the resulting forces from that. So I think, yes, we could use this model initially, but the results then wouldn't be used to kind of, again, inform any design decisions. It would be more to show off the framework of multiphysics solves coming together. And if we wanted anything more realistic, we would have to change the models here.
Thank you very much.
Okay, any other question? I think no. So thank you very much, William Ellis. Yes, sorry. And so we can switch to the second presenter, that is Mr. Alexander Farmakalides. And his presentation is regarding the wall system fusion reactor simulation with the CRATOS framework. So please.
Thank you. Can you hear me okay?
Yes, it's okay.
Yes, okay. So let me just share the screen. Okay, so thank you to the HPC Fusion Workshop for accepting my talk. It's a pleasure to be here. So I'm a PhD student at the Laboratory for Scientific Computing at the University of Cambridge. And today I'm going to talk to you about the CRATOS framework, which I've been developing over the last few years of my PhD. The aim of this framework is mostly to do instability and disruption simulations, so kind of related to the previous talk in that there is the need for, to simulate how does the plasma disrupt if there's termination of a discharge. And so we aim to create this framework to be able to do such simulations. There are quite a few slides that I'm going to have to get through, so please, I apologize if I'm rushing through them, but we can always come back and discuss afterwards. I'll be mainly rushing through the validation slides. I have quite a few of those. So fusion is hard, as we all know. That's why we're here, and that's why we have all these workshops. But so is the numerical simulation. Of course, we need numerical simulation. It helps us for device design and prediction. But even simulation is really, really hard. So what, even if you want to model some instabilities and disruptions from a fluid perspective, which is how we want to focus on doing things as an MHD fluid, you still have many issues with the disparate length scales, time scales, and highly nonlinear multi-material, multi-physics interactions. And not to, as if that was not enough, you have these very complex geometries, which this whole plasma evolution occurs within. So leading disruption codes and instability codes, for example, M3DC1, Jorek, and Nimrod, to name a few. These are very state-of-the-art codes, which are able to do a lot of very good simulations and have validated with experiments for things like ELMs and VDEs, edge localized modes and vertical displacement events. But they still have some limitations, mainly to do with the choice of numerical methods, the choice of mesh and coordinate system. So what are the limitations of these codes more specifically? For example, regions of the devices are isolated, so some codes will solve only for the scrape-off layer, some codes will solve only for the core. Also, they tend to lack shock capturing capabilities, mainly because of using implicit methods or finite element methods as well, which we see that are more and more important with the increasing complexity of the plasma conditions. Another issue is the use of field-aligned coordinate systems, which can make things very tricky in terms of generating the meshes to begin with. And when you have quite dynamic plasma evolution, tracking the mesh in that case can be very problematic. Alongside that, so sometimes the wall is not considered as something that responds to the plasma, which indeed it does in real life. It can have deformations, maybe elastoplastic deformations, and for sure we get currents induced in the wall. Another issue is the equation of states. So far in these simulations, an ideal gas equation of states is assumed for the plasma, which may not really be representative of the real thermodynamics that is going on. And one final thing is that with regards to fully three-dimensional non-axisymmetric devices, which is what tokamaks really are, these simulations prove to be quite challenging with the current simulation capability. So our aim is basically to address these points in a sort of step-by-step manner through the design of this code called CRATOS. We implement things from the ground up and go through step by step. So as was mentioned in the previous talk, that does take quite a bit of our time. But by doing this, we have the flexibility to add things as we go, to add physics, to change the way we solve for the physics, and it's very flexible in that regard. So significantly different from the current status quo, our code is based on a Cartesian frame of reference, fully Cartesian. We're going to solve for all the regions in one go using multi-physics and multi-material methods. So obviously Cartesian has limitations, one being how do you get around these disparate length scales, and for that we use adaptive mesh refinement, so using locally refined meshes which also move with the plasma dynamics. For this we base our code on the AMREX software, which offers the functionality for the Cartesian meshing with adaptive mesh refinement. For the fully nonlinear physics, so for having shock capturing capabilities, we use conservative finite volume methods. So conservative being a key word there, solving the equations, the governing equations in conservative form. We use multi-material methods which allow for a two-way coupling between the plasma and the vessel, and eventually we will be implementing more complex equations of state to properly describe the thermodynamics that occur at the plasma edge. So just to show some equations, these are the viscoresistive MHD equations in conservative form, and you have the viscous tensor, which has all your dissipation stresses, and basically we evolve the fluid density, the momentum, the magnetic field, and the total energy. As I mentioned, this is in conservative form, and we solve it using the finite volume framework. So shock capturing capabilities, we rely on basically proximate Riemann problem-based methods such as the HLLC or the HLLD Riemann solver, though this is we're not limited to these solvers, but they are kind of very good in terms of efficiency, robustness, and accuracy, and they have been they work well up to now. We achieve higher order accuracy using reconstruction techniques such as Wino and Mussel-Hancock with some Runge-Kutta time stepping, though there are plans to implement ADA in the future. Higher order is very important, especially if you're trying to model, with quite coarse resolution, but over many time steps. You really need the higher order to be able to preserve the steady states and capture the small dynamics that occur. For those of you that know, if you solve the MHD equations in conservative form, the magnetic field can really be an issue, and maintaining the divergence-free condition of the magnetic field. And for that, we use techniques such as the constrained transport or the mixed GLM approach, otherwise known as divergence cleaning. Multi-material interfaces, as I mentioned, so we use the ghost fluid method, which essentially allows you to implicitly assign embedded boundary conditions, and you're able to discretize on both sides of a material interface, and that works very well within the finite volume framework. And then again, for those of you that know about the intricacies of solving such simulations, so the reason why people would use a mesh which conforms to the equilibrium is because then all your forces align neatly on the mesh, and things like preserving a steady state is very easy. So for us, it's not that easy, but we use techniques such as well balancing, which can really help with preserving three-dimensional non-trivial equilibrium on a Cartesian mesh. This is the kind of overarching framework. I don't expect you to read through all of those individual points, but just to kind of go through it in a summary form. So we initialize the simulation, then we compute the grid, as in we mesh the grid based on the initial condition. So obviously regions that we are interested in, we will apply finer resolution. Then of course we will update the solution using first of all the ghost fluid method to assign the boundary conditions, then doing any source term updates and flux updates to the conserved variables. Now of course if you're using a Runge-Kutta integration, that will kind of change the way you're going through those sequences, but then ultimately we update to the next time step, and we do any post-update functions that we need to do, such as synchronization across refinement levels and such like. Once you've done enough time steps in your simulation, it's time to finish and basically terminate the simulation. And throughout the course of the simulation, you will output data which can be plotted and visualized. So just to go through some validation here. So one thing we want to do is start from very, very basics in ideal MHD, for example, and validate step by step and really demonstrate that the framework is able to capture the kind of theoretical nonlinear physics that you would expect. So here we have a Kelvin-Helmholtz vortex problem, and you can see there the vortex forming and the mesh refinement capturing the regions of interest around the edge. And basically, this simulation can also give key insights into the numerical dissipation of your underlying numerical schemes. One important thing here is that with adaptive mesh refinement, we're able to capture the sort of the vortex that you would capture if you were to use a higher resolution unigrid simulation. To sort of represent something more like a Tokamak plasma edge, we do the same simulation but in a very, very large domain, apply mesh refinement on top, and basically again just to demonstrate that with the AMR, the adaptive mesh refinement, we're able to resolve the small scale structures as we want. Of course, divergence error, as I was mentioning, is quite a pain with solving the equations in conservative form. But we show here that basically with the methods that we use, we're able to control that error to a satisfactory level that allows the simulation to basically carry on without any spurious oscillations or numerical artifacts. In terms of parallelization, we've demonstrated that the code can parallelize well. We use MPI to run on multiple processors, and we observe a good scaling. The plot I've shown on the right is by no means an optimized code, because that was not really the focus of my work, but even so, we still see a good scaling relation with MPI. Just to see the performance gains when you use something like adaptive mesh refinement, to just look at the top row there, a simulation using 2048 cells took 15,000 odd seconds to run, whereas running the same simulation but with 256 cells with 3 levels of AMR, so your effective resolution would be 2048, ran in just 700 seconds. So that is a massive speed up in terms of simulation time. In terms of multi-material, so we go through basically taking simple one-dimensional MHD tests and we put them inside of some rigid, perfectly conducting container. And then we show that we are able to match one-dimensional solutions, even with this rotated shock tube in 2 dimensions with the ghost fluid method, applying the reflective boundary conditions. Moving on to something more complex. So we take complex geometries like the ITER geometry or the ST40 from Tokamak Energy. And basically we take standard problems again and put them inside of these complex vessels and show that we're able to resolve the plasma dynamics. There's no sort of generation of spurious oscillations. Everything seems to be running quite well. And so on top of that, so we compare 2-dimensional axisymmetric versus running the simulation fully 3 dimensions to see that we do get the same result as we would expect. So in terms of the well balancing and preserving steady state equilibria, we compare basically how does the well balancing perform. So here I show that without well balancing and with well balancing for a large perturbation, so let's say you take an equilibrium and you introduce a large perturbation, the well balancing is able to capture this nonlinear evolution quite significantly away from the equilibrium. And interestingly, and why we need it, if you introduce a very, very small perturbation, so this perturbation is 10 to the minus 9 of the background equilibrium fields. If you don't use well balancing, the top there shows that you don't resolve the perturbation at all. Whereas on the bottom right, you can see that with well balancing, you're able to properly resolve the structure of the perturbation as you would want. So with this, we perform some long time simulations of perturbed equilibrium. So we take a screw pinch equilibria, which for sort of validation purposes, this should be stable in 2 dimensions, but unstable in 3 dimensions in certain configurations. So there on the right, you can see the growth rate in 2 dimensions basically reduces as you would expect. Whereas in 3 dimensions, the perturbation, which aligns with the plasma edge, eventually causes an instability to form a kink instability, I believe. And there on the bottom right, you can see how the amplitude of the mode grows with time and eventually causes the plasma to lose equilibrium. Some more validation, comparing with literature, also using adaptive mesh refinement to properly resolve the thing and validating that the well balancing works with that. So here is a diffuse Bennett equilibrium where we basically match the growth rates of the literature. Another part of my PhD was to implement a Grad-Shafranov solver to basically generate initial conditions that are relevant for tokamaks. I won't go into too many details into this because I don't really have the time, but essentially we had to implement one in the framework to suit the needs of the framework moving forward, so we couldn't just use one off the shelf. Then for validation, so this is an equilibrium of the ST40 tokamak. So I got some profiles and initial conditions provided by Tokamak Energy and was able to solve for the equilibrium in the ST40 vessel. And then match profiles that were produced by other codes. Just to show the effect of a mesh refinement once again, so adaptive mesh refinement, even with the Grad-Shafranov solver, is able to locally increase the accuracy of the simulation where it's needed. So then combining everything together, that's the whole point of the framework. So we take an initial Grad-Shafranov equilibrium, we apply a perturbation, and then we see how does this perturbation evolve in time. As a first case, we take an ELM simulation. So there's a popular CBM18 equilibrium. So this equilibrium was reconstructed within the CRATOS framework, and it involves a pedal stool region, which is quite sharp. And then this should cause an edge localized mode, which you can track in time and capture the growth rates if you need to. So again, everything is combined in one. And then on the bottom right there, for different toroidal mode numbers, you can see the growth rates, and we match very well with the elite code, which is a code which uses very, very different numerical methods to compute the growth rates. So that's reassuring that our framework is on the right track and is kind of doing the right things. As a final test case, I'm going to show basically what would happen if there was a sudden loss of power to a tokamak. This would never really happen, I guess, but you never know if there is a sudden power outage and all of your generators don't work for whatever reason. So essentially on the left we have the equilibrium, and you see that as time progresses, a shock front is produced, which propagates and slams into the vessel wall on the outer midplane. And of course we could then compute forces on the reactor vessel and what kind of damage that would cause. So what are the conclusions? So we've developed a three-dimensional Cartesian-based finite volume MHD instability simulation framework from the ground up, using up-to-date numerical methodologies, which is flexible to change as the needs arise. It's been thoroughly validated in multiple space dimensions, from the simplest of test cases to more complex ones as well. It's efficient, robust, and accurate. And essentially, there are still future work. Obviously, the equations that we're solving are not very complex in that you can do two fluids or multi-fluids. So that would be one of the goals in the future. Optimization of the GS solutions for future device designs is also one we're looking into. And also implementing resistive walls. So if you're evolving currents in the wall, how would that affect your plasma? And as I mentioned in the introduction, moving to a more complex equation of state. A couple of other things here, the main thing being that we want to also adapt the framework to a scheme that I also worked on during my PhD thesis, which was not implemented within the framework, but we would like to integrate eventually. Thank you for listening. Apologies if I overran a little bit, and happy to take any questions.
Thank you very much, Alexander. Very nice talk. There is time for questions if you have any. I have one. I have not very well understood if up to now the normal is doing such kind of analysis individually, and your approach is combining all together in this multi-approach schemes or in this CRATOS framework. Is it right? So...
Yes, sorry. So once again, I didn't quite understand.
If normally in the standard procedure, there is not a multiphysics approach. So in your new approach, you are combining together the different analyses that normally have to be done.
Yes, so the idea is to add complexity as we go. So another member of the lab who is contributing to the framework is implementing the resistive wall, for example, which will allow thermal and current loads to be modeled inside the vessel wall. We're also working on having different models for the scrape-off layer, such as a multi-fluid model. So these will all be coupled within the same framework and solved in a single simulation in one go. Without having to resort to sort of taking one code, transferring data to another code, solving there, and then back again.
Yes, nice. Thank you very much.
Welcome.
There is a question, I think, by Sharaf Khan. Is it okay to use Cartesian 3D in this case?
So I don't know which case is being referred to, if it's in general for the framework. It's something that hasn't been really investigated in the field because of limitations in the past, but we believe that with the current sort of techniques available, that yes, it is okay. Not only is it okay, but it could be beneficial because of the flexibility to the geometry. One thing that was made clear in the previous presentation is that meshing for complex geometries, when you're using something like finite elements, is really non-trivial and can take a lot of time and effort. Whereas with a Cartesian mesh, we're able to generate these meshes within seconds for fully three-dimensional complex reactor geometries. So there are huge advantages which can be taken advantage of for the Cartesian approach.
Okay. So if there are not many other questions, we can thanks again the speaker, Alexander Farmakalides, thanks. And we can switch to the third one. The third presentation is by Henrique Bergallo Rocha, and it's called Platypus, a scalable open source GPU accelerated MOOS app for multiphysics fusion simulations. So please, Henrique.
Thank you. Can you hear me well?
Yes.
Yeah, right. I'm just sharing my screen. Hopefully you can see it.
See. Yes, right.
Great. So yeah, my name is Henrique, everyone. I am from the UK Atomic Energy Authority, and I'm here to introduce Platypus, which is a software that we've been developing, and I'm going to claim that Platypus is a scalable, open source, GPU accelerated MOOS app for multi-physics fusion simulations. Right, so this is the outline of my presentation, and of course, as usual, we want to start with some motivation. So, and the motivation is basically this, right? There are a number of national labs around the world and also private companies that have intentions or projects to build their own fusion prototype power plants or experiments around the 2040s, right? And the UK Atomic Energy Authority is included in that because we have STEP, which has more or less that timeline for construction. And the point that I want to make is 2040 is really just around the corner. There's just really not that much time then to build enough real hard experiments in order to generate sufficient experimental data to fully qualify the components that we're going to need for the next generation fusion reactors. Now, of course, this being Fusion HPC Workshop, you know where I'm going with this. We need to do that digitally. We need the digital models in order to qualify these components, right? So what we need really is multi-physics simulation tools that are capable of modeling a range of fusion use cases spanning both time and frequency domains that we can give to engineers so that they can qualify, de-risk, assess a very complex coupled physics for their reactor designs and do that in silico, right? Regardless of any real physical experiments that might exist, right? So I'm going to do a little detour right now and talk first about MOOS and MFEM. I'm sure that a number of you have already dealt with either MOOS or MFEM or both, but just for completeness, I'm going to define them. So MOOS is a software. It's an open source parallel C++ finite element framework. It's developed by the Idaho National Lab in the US. And it's basically, a multi-physics tool that you can use to simulate and solve partial differential equations using, in a meshed environment. It has a large user community. As you can see, it has 1,800 stars on GitHub. And they have already validated extensively and thoroughly their physics modules in particular. And it is scalable. It works. It has been tested. MOOS has been tested up to about 10,000 CPU cores. And it scales well. And this is going to become a very important thing. It has a simple interface, right? You don't need to know the ins and outs of C++ in order to run a MOOS script, to run a MOOS simulation. You don't need to code at all in principle, as long as you know how to write a script, a MOOS script, which is fairly simple. Then you can run a MOOS simulation and gather some of the data that you need, right? So that sounds great. That sounds pretty much what we need, what I was talking about in the motivation. However, there are some issues. There are some barriers here. And in particular, I want to draw your attention to this part of MOOS, which is libmesh. So libmesh is the underlying mathematical finite element library that MOOS uses in order to simulate its multiphysics. However, the problem is that libmesh has some significant drawbacks, right? So, for example, it has limited support for hcurl and hdiv vector finite element types. You might know this as Nedelec and Raviat-Thomas finite element types. And if you've worked, for example, with electromagnetism before in the finite element framework, then you know that you need hcurl and hdiv finite elements, but libmesh has very limited support for those. Also, I'm going to talk a little bit more about this, but libmesh also only allows full matrix assembly. And something else that is going to become very important is that it has no support for GPU runs, right? And again, this is a HPC workshop, and a lot of you work with supercomputers. I'm sure you know that there are lots of new HPC systems coming online right nowadays, and virtually all of them are GPU machines, right? So we need these multi-physics simulation tools to be able to run on GPUs and scale well on GPUs, because otherwise, for very big, complex coupled systems, this might be a deal breaker, like for a lot of people. Right. So now let me talk about MFEM and what exactly is MFEM. And it does address a few of the issues that we've just mentioned with libmesh, right? So first of all, MFEM is also open source. It's also a parallel C++ finite element library. It's developed by a different lab in the US, by the Lawrence Livermore National Lab. It has a user community of about the same size as MOOS. But it does support high-order Nedelec and Raviat-Thomas finite elements. It supports a large number of performance solvers and preconditioners. It allows for assembly levels that are not just full assembly. It allows for element level assembly, partial assembly, and it does have GPU support. So you can run it with CUDA, HIP, OCA, Raja, and OpenMP backends, right? However, on the other hand, the problem with MFEM is that it's just not quite as accessible as MOOS. So you do need to to know a little bit the ins and outs of C++ if you want to code for it. There's a higher barrier for entry, right? And it's something that we can't quite expect of everyone who's going to want to run those big complex simulations to use or to know how to code for, right? So ideally, we kind of want the best of both worlds, right? It would be ideal if we could leverage the modularity, the interface simplicity of the MOOS front end with the power, scalability, and GPU support of the MFEM backend. And this is exactly what I'm here to talk about. So that is the idea with Platypus, right? So first of all, Platypus, you can see the link here. It's open source. Everyone can access, download, try things out with it. So do feel free to just go there. There's also some documentation that is being filled as we speak. So what exactly is Platypus? So first of all, Platypus is a Moose app, right? But what it does is that it bypasses Moose's libmesh backend that I talked about, and instead uses MFEM as the finite element backend. I'm going to talk a little bit more about this, but it has similar GPU performance as native MFEM. It does support MPI and OpenMP parallelism. Right now, we can run static and transient problems, in the latter case with only with implicit integration. It also does support, as I mentioned, bilinear form assembly levels of full, element, partial, and legacy. And if you don't know exactly what that means, that just basically means at what level of the degrees of freedom you're going to assemble your matrix, your degrees of freedom matrix. And it's kind of a trade-off, right, between memory and computation, right? So it is particularly important to find this balance if you're running on GPUs, because your problem can be very memory bound, especially for finite element, which tends to be quite memory bound. Anyway, Platypus is very much under active development, is a relatively new thing. We've been working on it for about 7 or 8 months. But there's been a lot of development in this meantime, and the version 1.0 is coming out soon. So let me just show you more or less how it would work if you wanted to run something on Platypus. And of course, I'm going to use the static diffusion example, which is very much the hello world of finite element. So on the left here, you can see the equation, the differential equation that we want to solve, and the mesh that we want to solve it on. And then on the right, you can see the script that you would pass on to Platypus if you wanted to do that, right? And for those of you who work with Moose, you're going to look at this and say, well, this is very much a Moose script. And it's as simple as that, right? So very quickly, let me just go through this, the different blocks that you can see here. So of course, you have a block for the mesh that you want to import, which is this mug. The problem here, we specified that it's an MFEM problem, right? You add the finite element spaces that you want. In this case, we just want an H1 finite element space with first order polynomials. You add the variables that you want to solve for, the materials and the property values that you want for those materials, the kernels that you want to, the actual equation that you want to solve for. And in this case, it's the diffusion equation. You can add the coefficients and then use those coefficients for boundary conditions. So in this example, Dirichlet boundary conditions. And then you can have a block for the preconditioner that you want to use and the solver that you want to use. And then the executioner block, in this case, it's a steady problem. And again, here, and this is very much a Platypus thing, you can define in which device you want to run this on. So it can be CPU. I could have put CUDA here or a HIP backend, and the assembly level, again, which can be legacy, full, element, or partial. And of course, you can get the outputs that you can visualize on ParaView, for example, if you want. So it's fairly simple, fairly straightforward to do. You don't need to know how to code for C++ if you want to run solve something like this, right? And that is the entire point. But the advantage is it runs on GPUs, it runs complex problems, it is scalable. And speaking of which, let me just very quickly go through some of the preliminary results that we have in terms of scaling and performance. So this is just a profile that I did on NVIDIA Insight systems running on GPUs. This is just to compare Platypus's performance with native MFEM performance. They're doing basically the same thing here. In both cases, it's a static diffusion example on the same mesh, the same number of degrees of freedom, same equation to solve. And you can see here that Platypus has a chunk here that hasn't been annotated by NVTX, and this is mostly because this is the part that is running on Moose, on the Moose side of it, whereas the MFEM side of it has been annotated with NVTX. We could go over each small block, but the point that I just want to quickly make is that, as you can see, the time the total time for the entire simulation in both of these cases takes about 14 seconds for Platypus and also for MFEM example 1. The solve step is less than 1 second. The building the bilinear forms happens on the GPU and is also a lot less than 1 second. So the performance is comparable in both cases. There's no clear significant overhead when it comes to using Platypus as opposed to native MFEM. Here we have some scaling of the number of degrees of freedom in our mesh and how the choice of assembly level affects this. So this is with a CUDA backend running on an NVIDIA A100 GPU. And you can see that in the part where we assemble the matrix, which is building the equation system, if you choose legacy assembly, it tends to be about an order of magnitude slower than its counterparts, the full element level and partial assembly. And this is to be expected because this is just to say that GPUs are fast because legacy assembly happens on the CPU, whereas these other kinds of assembly happen on the GPU. And you can see that at least with the molt step, which is the solve step, this relationship kind of gets inverted. So the closer you get to a partial assembly, the more computation you have to do in the molt step. And so therefore it tends to take a longer time. So the ideal thing is trying to find a balance between these two things. We also did a few preliminary tests trying out and comparing NVIDIA and AMD. So Platypus already runs on HIP on the AMD backend. In particular, we had access to NVIDIA A100s and the AMD MI300Xs. And this is a full assembly example, again, of the diffusion example with scaling the number of degrees of freedom. And there seems to be a number of significant overheads here with the MI300X, which show up on the full assembly, but not necessarily on the partial assembly results. The partial assembly are closer to what we expect, right? So you see a very clear scaling with the number of degrees of freedom, and also the MI300X is faster than the A100, which is what you would expect since it's a newer generation of GPUs, right? So anyway, just to talk about quickly what the future work, there's a lot to do still. So things that we want to introduce into Platypus. One is mesh updates, so adaptive mesh refinement to transient mechanical problems. We want to introduce Moose and MFEM transfers, so moving variables and grid functions around between sub-apps. Nonlinear problems, this is particularly important if we want to do superconductivity problems. Automatic differentiation is something that we're working on, and also the developers of MFEM itself have also been working on, and they should release something probably next year. And then matrix-free assembly, which is something that is relatively straightforward to implement. It just requires some changes to our continuous integration. So to conclude, we are not going to have enough experimental data by 2040 if we want to start building prototype fusion power plants or next generation fusion experiments. So we're going to have to leverage pre and exascale systems to get that data and de-risk our future reactor components. And Platypus does exactly that. So it enables the solution of large-scale finite element problems on CPU or GPU in the Moose finite element framework, but using MFEM as the underlying finite element backend in order to bypass the limitations that we have with libmesh. Some of the analyses that we've done with Platypus show that the performance is on par with native MFEM, in particular for GPU runs. And initially, we already have support for solving single variable study or transient linear problems, and the first formal release coming soon. Now, I do encourage anyone who's watching this, if you want to go in there, try to build Platypus, run things with it, just have fun with it. And then if you see any issues, if you detect any bugs, then do please let us know, because that would be very interesting. And yeah, I'll be happy to take any questions.
Okay, thank you very much, Henrique. Okay, so it's time for questions, if you want. Okay, there is a question by Sheraz Khan. How you compare this with COMSOL multiphysics?
In what sense? In terms of performance, because part of a lot of the work that we do in at the computing division at UKEA is with open source software, right? So we put a lot of emphasis on being able to do open source things, whereas COMSOL is closed. It requires, it's behind costly licenses. So I would say that, this is the main thing that we go for, but I'm not sure if you were asking about like performance or accessibility.
I'm also curious regarding performance or limitation of these codes that you can, for example, in which case you have tested, in which complex situation you have already tested. There is any limitation in terms of geometry or complexity of,
yeah, I mean, surely there are limitations because I've already mentioned some of the limitations. Some of the things that we've already tested are mostly thermomechanical problems. We are also testing Platypus out in the meshes that we have for Hive, which is an induction experiment that we have at UKEA. Recently, we've also been able to test on a relatively, a fairly complex mesh of masked U, which is a tokamak that we have at UKEA with gravitational effects. So while there are certainly still limitations and modules that we need to implement some of the things that I've listed at the end, we are already capable of simulating, fairly complex situations.
Okay, thank you. Jae-Min Kwon, please.
Thank you. Thank you for a very interesting talk. I'm actually not familiar with this underlying tool set, so my question is probably on this new framework and also the underlying one. So it depends, like for example, solving that kind of problem, ultimately that the scalability will determined it by this matrix solver, how they scalable in CPU and GPU. Could you a little bit elaborate the status of those matrix solver involved in terms of GPU parallelization performance?
Sorry, could you just repeat the question? It's a little bit muffled on my end.
So this question is simply how well this underlying matrix solvers scalable on both GPU and CPU, or sometimes, we want to utilize this hybrid, the computing environment. How are the scalability of those matrix solvers underlying this framework?
Yeah, the matrix solvers that MFEM uses are based on Hyper. And Hyper does have some very good scalability properties on CPUs and GPUs. It's been extensively tested, both in terms of like weak scaling and also strong scaling. So in theory, the best performance that we can possibly achieve in terms of the solve is the performance of Hyper, right? It's bounded by above, but it is very good. It scales very well is what I'm going to say. And Moose on that sense, on Moose's side at least, it has already been tested to scale well on CPUs up to 10 to the 4 cores.
Okay, thank you.
Okay, thank you very much. There is any other question? Okay, if not, we can thank again the speaker, Henrique. And thank you very much all for being here in the session. We can close this session. There is a break and there will be the last session in the main room at 15:30. Okay, so thank you very much all and bye-bye.
Hello, everyone. This is the last session of the day, which is devoted to advanced concepts and fusion materials. And in this session, we have two keynotes and one invited talk. And the first one is a keynote by Ann Lassa from University of Tennessee. She will talk about the development of multiscale computational frameworks to solve fusion material challenges. Welcome, and you have 35 minutes for the talk, and then we will have 10 minutes for question, okay? The floor is yours.
Thank you so much, Adilberto. And thank you everyone for attending the talk, to learn a little bit about the approaches that we've taken to address fusion material science challenges. As you can see, this is a group effort, and I want to thank as well each of the co-authors for their contributions and for their help preparing this, really. So, there we go. There we go. That seems to work. So I want to start today's talk by introducing a little bit the kind of challenges that we are dealing with. So the multi-scale characteristic of plasma surface interactions, as well as fusion neutron radiation, and how we've approached this through multi-scale modeling. And I will be spending most of the time showing 3 case studies. The first one, how we've addressed mixed material mixing, such as beryllium tungsten mixing through atomistic work and how that feeds into the mesoscale. The second one, how we couple these mesoscale methods into larger systems. And a third application on how we are preparing for the future, ready for the exascale. So I would like to start by just introducing briefly plasma surface interactions, even though I think most of the audience here is well familiar with it. The interaction of surfaces exposed to plasmas with the energetic ions and neutrons that come from plasma really leads to a range of damaging processes such as erosion, gas retention, changes in morphology of subsurface composition, as is depicted here in the figure. These processes really change the properties of the material that is exposed to the plasma. That might be lower melting temperatures, that really compromises the performance, the durability, such as, through erosion, we are thinning out the walls, and as well as safety, because we are retaining fuel, for example, in the material. Not only compromises the performance of the materials, but also of the plasma, as it introduces, for example, erosion introduces impurities that can radiate some of the heat, which is fine in the boundary, but it's a bigger issue in the confined core plasma. Large emitted particles, such as, large dust particles can cause disruptions, and, changes in how the fuel is trapped and recycled can change as well the local plasma conditions. So essentially, plasma surface interactions are not only necessary to understand the evolution of the materials and predict how long they will stand, but also to accurately predict the plasma performance. As I said, these plasma surface interactions are not only multi-physics, because we have to, account for material physics and plasma physics and their interaction, but each of these, as you can see here depicted on the right, are multi-scale in nature. So we have processes that range from the atomistic all the way to a macro scale, and they are all closely interlinked. The picture is very similar, actually, for materials subject to irradiation, that is from high energy ions and neutrons. We have a picture that is equally multi-scale from, for example, defect production in the atomic scale, all the way to microstructural changes that can, really directly affect the performance and, for example, the fracture toughness of the device, of the structural materials and functional materials. So how do we address this? Our approach has been to do a bottom-up multi-scale modeling. So we do start generally in our group from, DFT-like high fidelity models that inform the atomistic modeling through molecular static and dynamics, and that really builds basis for the cluster dynamics methods that I will show are really our workhorse in bridging the skills from the high fidelity atomistics to the experimental. And as I will be showing here, we use these atomistic methods to understand, for example, material mixing, which is one of the examples I'll be showing, as well as the gas dynamics in materials. So, how fuel is trapped and, things like helium-hydrogen synergies. And that multiscale process figure that you saw really translate to a multiscale modeling figure that is shown here for plasma surface interactions. So how these DFT methods, molecular dynamics methods inform really the mesoscale method Xolotl, that is one of the cluster dynamics methods I'll be showing today that we use regularly. And the picture is very similar again for structural modules and subject to high energy radiation. And the goal of the project is, to start transitioning from this interpretation capability to having a more predictive capability. So with that, I would like to then introduce briefly each of the workhorse codes that we've been using. And the first one is Xolotl, and this is a continuum cluster dynamics code that we use to model plasma exposed surfaces, essentially plasma surface interactions. In this case, and as I said, we are essentially moving from this atomistic view to the continuum view. So in Xolotl, the material is represented by a grid. In this case, I'll be showing that represents tungsten. And in this grid, what we have is instead of simulating each atom here, what we simulate is we have a concentration of clusters at each grid point. These clusters can contain interstitial vacancies, helium, hydrogen, and a mixture of thereof. And then the time evolution of these concentrations is really given by the drift diffusion reaction equation, where we have an influx, we have the drift diffusion time, and then we have the reaction between the different clusters. Xolotl was developed using C++, uses PETSI as a solver, and supports MPI, and uses COCOS for performance portability. The second of the workhorse models that we've used is a final volume stochastic cluster dynamics model. And this is used to address damage accumulation in tungsten. Essentially, in this model, what we do is we recast the coupled differential equation system as a stochastic framework, and then we use kinetic Monte Carlo methods to solve it. And so it really, it executes one defect per Monte Carlo cycle, and here you can see how it allows finite volume fluctuations. Now, with that brief introduction, I would like to move on to the bulk of the talk, which is showing the 3 case studies. The first one, the atomistic study of beryllium tungsten mixing and how this informs Xolotl. The second case study is how you use Xolotl in this integrated plasma surface modeling, as well as how we apply uncertainty quantification methods to learn a little bit more about this integrated plasma surface interaction model, and how we couple stochastic cluster dynamics methods with crystal plasticity models to address simultaneous deformation and irradiation. And I will finish the talk showing a little bit how we are preparing for the future for the exascale era. So starting with the tungsten beryllium mixing, any good atomistic work starts with good potentials. That's, I think, well known to the audience, most of the audience. And so in this, excuse me, in this project, we start with the development of with interatomic potentials, which are really the main source of uncertainty or inaccuracy, and often don't exist for materials. They are very difficult to develop. So our approach is to use a SNAP. This is a machine learning method for developing interatomic potentials. And essentially, it's a machine learning method where we can feed DFT data or any other information we may have and let the machine leads work. This allows us really to develop potentials with near quantum accuracy, but we can then use them at molecular dynamic scales, and allows us to develop potentials for traditional difficult materials, like it's actually the tungsten-beryllium system. Once we have the potentials, we can then perform molecular dynamic simulations that, for example, here we're showing helium implantation in a tungsten surface compared with a mixed tungsten-beryllium surface. And the hope is that this kind of work can inform eventually and help us explain how, for instance, when we have a mixed deuterium-helium plasma, we see that tungsten bonds formation that everyone is probably familiar with by now. Whereas when we inject beryllium, we suddenly see that being suppressed. And so once the potential was developed, we applied it to simulate beryllium deposition on tungsten in their mixing. We learned quickly that, just as predicted by TFT, these two are actually dynamically driven or favorable to mix, but there's not a good kinetic pathway, which means that we essentially need some kind of beryllium interstitial or a tungsten vacancy that kicks off that triggers that mixing. Once the mixing is triggered, as we can see here, the two materials do mix, and they tend to mix towards that beryllium to tungsten ratio of 2:1, which is the thermodynamically most favorable. With that information, we can develop then a 1D equation for diffusion of beryllium in tungsten, which is the driving force of the mixing in tungsten and tungsten beryllium intermetallics. And so we parameterize this with the atomistic work that we've shown and some more that we did. Here you can see, for example, the diffusivities of beryllium in the different beryllium tungsten intermetallics and some more, formation energies, for example. And with that parameterization, we see that our model seems to match experiments or agrees with experiments fairly well for that. We do want, this is just for the 1100 or it's 1000, I think. Yeah, 1000 Kelvin. So we do need to start testing a little bit the temperature dependence of the layer thickness growth, really. And this formulation, perhaps more importantly, is ready to incorporate into shallow dose so that we can address hydrogen and helium implantation not only in tungsten, but actual beryllium tungsten mixtures. And it's easily transferable to other low Z impurities. So the next step for this particular system is really starting to parameterize the hydrogen implantation in tungsten. And this is some preliminary work that I will be showing. Some initial hydrogen implantation in this beryllium tungsten intermetallic shows that the shallower hydrogen implantation and much higher sticking of hydrogen when beryllium is present. We think that this is due to a couple of factors. The first one is the beryllium is closer in mass to hydrogen tungsten, and therefore it's a lot more efficient, at the slowing down hydrogen. And there's we notice some more absorption of hydrogen on the intermetallic surfaces, in particular in the tungsten beryllium 2. In that hints at some, differences well in the structure and the chemistry of the systems. So I've shown you a little bit how we inform the mesoscale models such as Xolotl, and I would like to show next how we actually use this in larger systems by integrating it with plasma models. And that's what we did using the IPS framework, integrated plasma simulator framework, where we integrated starting with SolPS, which is a code to solve the boundary plasma characteristics. That with those edge plasma conditions, we used HPEC, that's a particle in cell code, to resolve the sheath characteristics and, more importantly, the impact energy and angular distributions. And using fractal triangle, which is a binary collision approximation code, to give us the erosion rates as well as reflection rates. We use the impurity transport guitar to calculate tungsten erosion and transport in the edge plasma. And essentially, all this package, what gives us is the radiation conditions on the surface of a plasma-facing component. And with those irradiation conditions, we use fractal trial, again, the same Farmakalides approximation code, to give us the sputtering rates at each location, as well as the implantation profiles of whatever comes. Might be the tungsten as well as the background plasma. And we loop the two to have a time evolution of the surface. We've applied this technique successfully to interpret and predict plasma surface experiments in current devices such as WEST, as well as future Tokamaks, such as ITER, which is the example I will be showing here. And what I will be showing are just a couple of highlights from applying this workflow to modeling the ITER diverter during full power burning plasma operations for an initially pristine tungsten surface, as well as a diverter pre-damaged by helium plasmas. And so the first of the highlights I would like to show is that we noticed how in the beginning of the simulation, this is for a pristine tungsten surface, the near surface concentration of tritium and deuterium drop very dramatically. And that was for a location of high heat flux. Now, it wasn't as dramatic for a location of a lower heat flux. And so by comparing the two, what we noticed was that the concentration is dropping as the temperature is rising. So it really is taking the value expected for the temperature at that time. And this is due to the higher diffusion of deuterium and tritium as the temperature rises, mainly outgassing because it's so close to the surface. A second highlight that I would like to show is related more to the role of the pre-damaged by helium plasma, which we've learned that it leads to strongly bound shallow retention of tritium. We compare here the exposure to burning plasma operations when initially pristine tungsten substrate with one pre-damaged by helium plasma, in this case in Pisces. And what we see is that that the deuterium and tritium are retained closer to the surface when it's pre-damaged by helium compared to the pristine tungsten diverter, but the bulk concentrations are much lower. This leads to a total tritium content lower when there's a helium pre-exposure than for a pristine tungsten substrate. Another perhaps more nuanced result that we notice as well is that this is for a location exposed to a net tungsten redeposition. So essentially we have a tungsten layer being built. And in these cases, even small quantities of helium can trap in those building layers and can self-cluster. Those bubbles can burst, leaving behind vacancies that are then refilled with deuterium and tritium. And essentially we have tungsten layers with these little deuterium tritium bubbles, or like mini clusters inside being built that lead to near surface tritium accumulation. And this is really only observed in the long term, after tens of seconds, which really showcases the capability here of modeling tens or even 100 seconds of ITER burning plasma operations, but starting from the plasma all the way to the material. And so this is for steady state plasmas, since we are only evolving the material. We then took the workflow and we reformulated it to introduce time dependence, which now allows us to address also transients. And in this case, it's a simplified version of the workflow, where we start with SOL-PS, which provides plasma temperatures and angles, the fractal trying to calculate the sputtering yields and reflection yields, as well as implantation profiles. With that, particle heat fluxes coming from the plasma, then Charlotte evolves the material composition, which provides which together with fractal trial provides the prompt recycling, or really reflection of plasma particles, as well as the total recycling, so accounting for the long-term recycling, and changes in temperature of the wall back to SOL-PS, and we loop this over time. We applied it to some D3D plasmas, but what I'll be showing here is a recent application to addressing recycling in the ITER diverter during ELMS. These are hydrogen plasmas expected for early ITER operations. We've modeled both attached and detached conditions, and I will be showing simulations for 5 locations. You can see here near the strike point. And in this case, we are starting with a tungsten substrate pre-damaged by previous helium operations. And we're testing 2 different ELM frequencies. One is 1 millisecond of an ELM followed by 1 millisecond of an inter-ELM, and the other one is a 20 millisecond inter-ELM. And initial results hint that even though the plasma conditions are very different for the 4, attached, detached, 1 millisecond inter-ELM, 20 millisecond inter-ELM, for those 4 cases, even though the plasma conditions are very different, as you can see here, these are particle fluxes, and these are heat fluxes, we see, essentially orders of magnitude difference. Somehow, the hydrogen content and the concentration, the result concentrations, are somewhat similar. There's perhaps this one case, the one attached with longer inter-ELM durations, that, it's slightly different, but overall, they are remarkably similar. And so our initial hypothesis is that the pre-damage is really driving the hydrogen content and the depth profiles. This is just an initial assessment, and really to confirm this hypothesis, what we need to do is to run the same simulations with a tungsten divertor that is not pre-damaged. And we are also interested in running the workflow without the ELMs to isolate the role of ELMs as well. So I would like to show now how we've looking a little bit deeper into the system to assess what are the main parameters that are driving the results, in particular in this fractal transsoluble coupled system that is modeling material. So I'll be showing, instead of the ITER simulations, we've applied this also to model helium plasma exposures in the linear device spaces. And so I will be showing a little bit of work that we've done in assessing what fraction of the output variability can be attributed to what set of input parameters. This is called variance-based sensitivity analysis. And this is important in starting to build reduced models or surrogate models that are a little bit computationally more affordable than running the full high-fidelity models that we've been talking about so far. There were a couple of particular challenges for this case. The first one is that model evaluations are expensive, and the dimensional space that we needed to explore is rather large. We had 19 input parameters that we wanted to explore. So in order to start exploring a little bit those surrogate models, we construct them by polynomial chaos expansion. So the first thing that we did was check how these surrogate models capture a little bit key outputs, and the key outputs in this exercise will be the surface growth predicted by the system, as well as the helium retention. And we see that they do fairly well. You can see in blue the training data, in red the validation data, and we see a fair representation. The second thing we do with the system is to look what are the key input parameters that drive the outputs. And for surface growth, we see that the surface binding energy really drives most of the surface growth, controls most of the surface growth. And for helium retention, the migration of energy of single helium atoms really dominate time evolution of the sensitivity indices. So really, that's what we learned from these initial exercise, where we see that the surrogate models do fairly well, and very few parameters explain most of the output variance. So that's fairly good outcome in a way. We are like, okay, a few parameters will do. But these surrogate models based on the high fidelity models are still too expensive. So what we want to do is then take and see what's the smallest good enough simulation we can run to make it cheaper, really, because computationally less expensive. So we apply what's called multi-fidelity UQ. So essentially, we start with what we run is a hierarchy of low to high fidelity models. And what we do is, given a set of fidelity levels, we compare one to the next. And you can see here as fidelity parameters we use in Shuttle the network size, which is really related to the largest vacancy cluster allowed in the Shuttle network. And then the grid size, which is related to the computational domain. And again, we focus in outputs as outputs in surface growth and limit retention. And what we do is for these two fidelity parameters, what we do is run 100 randomly chosen values for the 19 parameters that I showed before. And unfortunately, what we learned in this case is that there's a lot of convergence. You can see here as we increase the grid, the 19 parameters seem to scatter. And if we compare one grid size to the next, the results don't necessarily really converge. In addition to that, the speed up factors are about 2 to 3 at best for surface growth, none for retention, as for the smallest networks. And for for varying the grid size, we do see a speed factor of less than 2. So it really seems to be that the multi-fidelity UQ is not the right approach for that system. So moving on to how are we doing with time, Chairperson? Oh, that's okay. Moving on to then the next case study, which is coupling of the crystal plasticity and stochastic class dynamics models to address simultaneously deformation and irradiation in tungsten. What we've done is we've coupled a crystal deformation, a crystal plasticity model with components for the elastic and plastic, with elastoplastic decompositions used to model the crystal deformation, and a stochastic class dynamics method that allows you to simulate irradiation, defect reduction, diffusion, and their reactions. And the coupling of the two models is really bidirectional. The stochastic class dynamics method provides with the defect densities and sizes that the crystal plasticity model needs to quantify irradiation hardening. And the crystal plasticity model provides the evolution of the dislocation densities, which updates sink strengths and defect absorption for the stochastic class dynamics method. We validated first each of the models, and then I will show the results for the coupled system. When we validated the crystal plasticity model alone, we explored 3 variables. The first one, the strain rate, the loading orientation, as well as the temperature. And as shown here, we can see a decrease in yield strength with temperature, for the different loading orientations. We also validated the stochastic class dynamics model for these experimental-like conditions. And what we see that the irradiation results in hardening consistent with the dispersed barrier hardening behavior. As shown here, we see increased concentrations of the size, concentrations and size of the vacancies and subcluster interstitials. We see that the concentrations especially increase for the lower temperatures, and the average vacancy and self-interstitial cluster sizes increase for the higher temperatures. If we couple the two, now the system shows how it hardens with irradiation. Essentially, we see the defect on defect separation and yield stresses shows how the system hardens with irradiation, as shown here. And we see how the inverse of the defect spacing really depends now on the crystal orientation, because we have that crystal plasticity model that allows us to resolve that. And we can obtain results such as, the differential yield stress. So we can see how the yield stresses differ for the irradiated and unirradiated cases. And with that, I would like to move to the last chapter, which is showing a little bit how we are preparing for the exascale era. We've done that in collaboration with the ECP EXALT project, which develops powerful atomistic simulation codes for the exascale computers, and it really addresses two main challenges. The first one is that the efficiency of legacy MD implementations is often suboptimal in GPU architectures. And the second one is that it often, exascale computing often enables larger systems, but not necessarily longer timescales. So to do the latter, the EXALT project has developed parsplice, which is a parallel in time method to enable essentially, longer timescales in atomistic simulations. And this project, has managed to improve a 25-fold the performance of machine learning potentials, the snap potentials that I showed you before in modern GPU systems. And another highlight of EXALT project would be that they managed to get a nearly 400-fold improvement in performance of these MD simulations in terms of timescales in modern machines such as Frontier. That would extrapolate to an over 500-fold acceleration over baseline if they were to use the entire Frontier machine. And with that, I would like to come to the conclusions, where I will wrap up a little bit saying the same as I did in the beginning. I have presented our multiscale modeling approach to addressing plasma surface interaction and irradiation effects in fusion materials. We use a bottom-up multiscale approach where we use atomistic methods to inform mesoscale models, both the stochastic and cluster dynamics methods that are our workhorse really to integrate the different scales. We have shown examples of critical challenges in fusion, such as the mixed materials, in this case, beryllium tungsten mixing, and how we incorporate this information into mesoscale. I've shown you then how we use these mesoscale methods in larger systems to address the evolution of plasma-facing materials in future devices, and how we apply uncertainty quantification methods to learn a little bit what are the most important parameters in our system. I've also shown how we couple the cluster plasticity models with the stochastic cluster dynamics methods to predict, hardening and changing mechanical properties under irradiation. And I've shown a couple of slides and highlights how we're preparing for the future. Now with that, I would like to acknowledge all the funding that has come to this work, as well as thank you for your attention.
Thank you very much, and you are perfectly on time.
Wonderful.
And now we have time for questions. You can raise your hand and make your question, and you can type in the chat. We don't have a question yet. May I have a question myself? And you said that the hydrogen accumulation is strongly dependent on the previous damage of the wall material.
Yes.
And we know that the plasma wall interaction condition affect strongly to the plasma performance. So can we expect that in reactor plasmas, due to this change with the damage of the wall material, can we expect a degradation of performance or a clear tendency with respect to the present plasmas?
Well, so I think that's exactly what we're trying to get at in with the time-dependent workflows. Because these are the steady-state workflows that are so far a little more capable of addressing long-term evolution. but they don't have any feedback into the plasma. And so this is exactly what we're trying to start to address a little bit with these time-dependent workflows to see how the wall response in, for example, pre-damaged tungsten surfaces affects, what we're inputting into the plasma, so what recycles. And that's exactly what we are trying to start to address a little bit here. And as I said, we're interested in the ELMs, how the ELMs affect the material and the pre-damaged material, but as well without ELMs to see what kind of capability, how long can we run? Because you can see that these timescales are sub-seconds. So we are not seeing really the long-term evolution here yet. And that's because, once you start feedback, these time-dependent workflows are significantly more expensive to run than the steady-state ones. So that's the kind of question we are really trying to start to target. And we are trying to explore. We have, and there's a publication out there exploring a little bit the coupling frequency of the codes. So what's the loosest coupling that we can afford ourselves to have without altering the results, right? Because the less often you have to couple them, the cheaper it is to run the system, even though you're still doing time dependently. And so we are exploring that kind of internal parametric. We are performing these kind of parametric studies in trying to really address, essentially the combination of the two, right? What we want is the resolution of this system in the timescales of this one. And that's really, I think, where it's at. And let's see how far we can push these methods. I agree.
Okay, thank you very much. We have a question in the chat. It's a long question. Maria Jose Caturla asks, in this transfer, very nice presentation, said, in this transfer of information to larger models, it seems we are mostly transferring defect densities and sizes to the larger scale models. Is it thus correct?
Maria Jose, would you be able to come online and clarify what you...
Yes, I'm sorry, I couldn't find the hand to raise my hand. I'm sorry about that. So my question is, do you think there is any other information from the atomic scale that we need to transfer also to the larger scale models? Sort of like the strain of the effects. I mean, there's some different groups that are working on that, transferring information about strain, about maybe the temperature that is because of the deposition of energy and so forth.
Are you asking about a particular system or just in general?
In general, as a scheme of this transferring of information from one model to the other.
Well, I think the approach we've taken is system by system. So, I showed that ICFRM, which I decided to drop here due to time constraints. Also, how we address the helium bubble formation and growth in tungsten, and how we transfer that also into Xolotl through a bubble bursting model. So I think it is very system to system, and that's the importance of starting with the atomistics, is that you can look at what are the key parameters for each system at the atomistic level and focus on that and transferring that into the mesoscale. Now, of course, you could be missing effects that come in the long term, but that's a risk that I don't know how we would solve. Essentially, the long-term evolution of the atomistic methods is just a terrible, it's a very, very big challenge, and hopefully this kind of EXALT work can help us address to some degree by improving the performance of not just running bigger systems, which also is important because we want to make sure that, we are not missing anything that comes with larger, length scales, but also time scales. So I think there's something to be learned here by running longer, but also we just have to rely on learning, I think, on the atomistic scale, each method or each system, and then transferring that into the mesoscale, or incorporate really that into the mesoscale.
Thank you. Thank you. It's very nice.
Thank you.
Very nice work.
Thank you.
Mary Mancinen has another question. Thanks a lot for the nice talk. How do you see the potential of material simulations to guide the design of future experiments on fusion materials, such as those of IFMIF-DONES?
So I think, these high fidelity models allow us to do a lot of physics and really learn a lot. But I think in terms of, and this is more my personal view, it's not a project view, I do really think that if to do serious design work, we need to start thinking more about reduced models. And I think, this is essential. This multi-scale approach is really, I think, essential for that work. Wait, hang on. This is what I was looking for. And this is where really it comes, the reduced parameter models. I think we need to do this work, what we're doing now, to build the foundation of reduced models. And we do need to start doing reduced models, even if they are not perfect, to see how they compare to the higher fidelity work that we are showing here, and many other people are doing around the world. But I think ultimately for design work, that's what you need. You need a lot more efficient systems, not something that needs, supercomputers to run. That's my view. I think we need to continue working in all these fronts to learn more, but ultimately, to design, even for pre-design studies, these models are not efficient enough, is what I think.
Okay, I have another question myself. You said that you use the surrogate models using information from the high fidelity simulations, but then you said that high fidelity simulations are not necessary. You don't need so much fidelity, let's say, if I understood properly. So can you train or use these surrogate models with information only from low fidelity simulations that are less expensive?
So that's what we wanted to do. That's what we were trying to figure out. It's like, what's the smallest good enough simulation we can run? But unfortunately, and this is what I was trying to show here, maybe it wasn't very clear, but so these surrogate models, as we start to get smaller and smaller, we are losing fidelity, essentially. So these polynomial chaos expansion surrogate models are not fitted for our system, is what this is showing us. So there's a group, or part of our group, working on UQ, looking at other surrogate models, perhaps, and other methods. But what I wanted to show here really is that the surrogate models at lower fidelity, at higher fidelity, they are doing a great job, or a pretty good job, right? Like, it can be improved, but it's a good job. As we start to go down in fidelity, they are not capturing the system that well, and they are not giving us a speed up levels that would be worth it. So essentially, we wanted to do what you suggested, but it doesn't seem to be working for this system.
Okay, thank you. Okay, we don't have any more questions. So thank you very much, Anne, for this nice talk. And we go for the next one. The next talk is by Rogerio Jorge, that comes from University of Wisconsin-Madison. This is an invited talk, and the title is Design of Accelerators with Simple and Flexible Coils. I don't know if Rogerio is over there. Are you prepared? Yeah, okay.
Yes, hi, can you hear me?
Yes, very, very well. So, Rogerio, welcome to the workshop, and you have 25 minutes, then we will have 5 minutes for questions, okay?
Okay.
You can start whenever you want.
Okay. Hi, everyone. Thank you for the opportunity to present this work. This was a work developed this year with a collaboration between Wisconsin-Madison, the Flatiron Institute at New York, and the EPFL University. Oh, sorry, I didn't get the affiliation correct. So Joachim Luis from EPFL University in Switzerland. And this code uses this work uses the SimSoft code. So I also acknowledge the work from the SimSoft team in developing the code needed to run all these simulations. The results are in this paper that has been published recently by Physics of Plasmas, and all the scripts and results are also on GitHub under the repository Simple Coil Paper. We added to SimSoft, the solid optimization code that is open source and online, a simple example in order to have people that don't have a lot of experience running all of these stellar optimization scenarios to just install SimSoft, run an example, and have an optimized stellarator. Okay, so what is single-stage optimization? I'm going to show here on the right a movie that tries to showcase what happens during an optimization like this. Before going into stellarators and coils and whatnot, I think it's nice to have a visual representation of what we're talking about. So I'm going to play this video, and I want you to see the fast change between the coils and the plasma that happens during the simulation. So what the optimizer is trying to do is changing the coils at the same time as it's changing the plasma with some sort of constraint between them. So that whenever we change the coils, they do not reproduce exactly the field lines that go into the plasma. So we need to add a penalty to minimize this difference between the two. So as time goes by, this penalty becomes smaller, and the coils reproduce the plasma better and better and better. That's the metric you see here that I write as B.N divided by B. So if we have a flux surface, by definition, all the field lines are tangent to that flux surface. So if I trace a magnetic field line from the coils, they should reproduce exactly this surface. Therefore, the dot product with the normal vector from this surface should be 0. And then I divide by B just to normalize and have a relative measure of this B.N at each point along the stellarator. So the overall penalty we're using is the sum, or better yet, the integral of all of the B.Ns divided by B on our stellarator. As you'll see later, there are also some metrics that we put in for better confinement, for simpler coils, but overall, this is what guarantees that the coils are always linked to some sort of plasma shape. Let's talk then about stellarator optimization. Stellarator optimization is usually divided into 2 stages. Stage 1 is trying to find the magnetic field equilibrium, but that solves the ideal MHD equations in order to confine a plasma. This magnetic field equilibrium still has a lot of freedom because stellarators can be twisted in an infinite amount of ways. And these are some of the few metrics that we try to minimize during this optimization. One of them is quasi-symmetry or quasi-isodynamic. These are big terms that they basically mean that we confine trapped particles, which is essential to have a good plasma and essential to confine alpha particles from fusion devices. This is usually termed alpha particle confinement, and also is related to neoclassical transport. Another metric is turbulence. This is still being investigated. How can we decrease anomalous transport in stellarator devices? And there are some ideas on how to add that metric to the optimization. Another one is aspect ratio, so that we have at least some measure of what's the volume inside our stellarator. Sometimes the optimizer can have a very compact stellarator with a huge volume, or sometimes a very small and thin stellarator with a very small volume, depending on the optimization target. So at least then we set a given aspect ratio, and at the same time, we usually set a major radius. And finally, iota, which is 1 over the safety factor. This basically means that I want a stellarator and not a tokamak. A tokamak would be just an axisymmetric solution. That axisymmetric solution satisfies some metrics. It can satisfy the metric of aspect ratio, quasi-symmetry, but it's not one of the solutions that we want. We want a solution that is twisted, that looks like a stellarator. So what are the 3 different types of stellarators that I'm going to talk about? These are called homogeneous stellarators. These are types of stellarators that are known to confine particles, they are known to have low neoclassical transport, and they're often characterized in 3 types, depending on how the magnetic field strength looks on the boundary. Here, the magnetic field strength is plotted with these colors, red to blue, and in a quasi-axisymmetric stellarator, you can find a closed loop of the magnetic field strength that goes around toroidally. This is very similar to a tokamak, that's why it's called quasi-axis symmetry. In quasi-helical symmetry, it goes around helically, so you can always find a closed loop of the magnetic field strength that goes around in a helical manner. And finally, quasi-isodynamic is a magnetic field strength that closes in an opposite way of a tokamak, that closes poloidally. Examples of quasi-axis symmetry is the mu stellarator being operated at PPPL in Princeton. In quasi-helical symmetry, you have HSX here in Madison, and quasi-isodynamic is, for example, the W7X device in Germany. All of these have different orbits for trapped particles. The quasi-axis symmetric one has trapped particle orbits that look very identical to the tokamak case. For quasi-helical stellarators, if you make a small coordinate transformation, you also find orbits that are similar to the tokamak case when you take into account the helicity of your coordinates. But for quasi-isodynamic stellarators, the coordinate transformation is not as simple, but still we have particles that are confined and close to a flux surface. What does an optimization function look like for stage 1 stellarator optimization? It can be quasi-symmetry or quasi-isodynamic with some measure that we call the residual, some aspect ratio minus a target aspect ratio, and iota minus a target iota. And the degrees of freedom are the boundary degrees of freedom. Basically, we just change the boundary shape, and because the ideal MHD system of equations is a system of PDEs, once we have a boundary condition for a fixed flux surface, then we are able to find all of the field inside of that boundary. This is an example of a quasi-axis symmetric solution, which doesn't have perfect quasi-axis symmetry, but has a very good quasi-axis symmetry. These are all of the modes in Fourier space of the field strength that are quasi-symmetric or non-quasi-symmetric. So you see here this purple line, that is the term that is not quasi-axis symmetric, and that's basically what we're trying to reduce whenever we do a quasi-symmetry optimization in stage 1, and this is the metric that we target. This is very akin to having low neoclassical transport, or basically charged particles that have, on average, 0 radial velocity. Let's look at a very simple example of a stage 1 optimization. This doesn't use any fancy optimizer, it's just a parameter scan. Here I have a rotating ellipse. And this rotating ellipse, the only thing I'm changing is a single parameter, and that parameter is wherever the ellipse is at phi equals 0. So at the given plane, I'm just making the ellipse go left to right, and I let all of the other parameters fixed. And because this is a rotating ellipse with a 4 symmetry, with 4 field periods, then everything else is constrained. If you look at quasi-symmetry residual, it has a nice decreasing line in the global minimum. There are other functions or other optimization functions that we're not considering here that are not as smooth, that are very noisy. For example, the loss fraction of alpha particles. Another function that might be very noisy is the one of quasi-linear fluxes for turbulence. And if we consider nonlinear turbulence fluxes, they're also very noisy, so we're not considering those for now. Stage 2 optimization deals with coils. And with coils, we have to balance two things: coil performance, so the coils that are accurately reproducing the magnetic field, and coil complexity, coils that are very, very complicated. This is a very challenging feat because we can find many sets of coils that reproduce exactly the same magnetic field. And this is an example of why this happens. Let's say that we have a W7X boundary, and we try to get coils for W7X. If we extend a coil a lot to the left, and then it goes back almost through the same path to the right and then to the left, what happens is that the fields nearly cancel, and the magnetic field on the boundary looks pretty much the same. Therefore, the optimizer can lead to very complex coils with fields that barely cancel, because the coil set is not unique. Also, as we tend to make coils far away from the plasma, they tend to become more and more complicated, which is a problem because we need a blanket and a shield between the plasma and the coils, and this distance has to be very big. Therefore, coil optimization tries to balance all of this at the same time. What does an objective function usually look like? We have the first term, so the integral of b dot n, that is basically saying that I want my field lines to follow whatever plasma boundary I have. Then the coil length, the distance between coils, and the coil curvature. These are trying to make, if I have a coil length that is small, it usually tends to have simpler coils. And if the coil-to-coil distance is larger, then the coils are easier to manufacture, and we need a smaller number of coils. And finally, if we have a smaller curvature, they're also simpler coils. How does optimization in stage 2 usually work? We start with some circular coils and try to approximate the boundary. Therefore, the term with b dot n is very, very large. So we let the optimizer change the coils to decrease the b dot n. So we change the coils, we see how the field lines look like, and then if they align with the flux surface, we have a very good solution. In a single stage, how the optimization usually goes, we put everything together and we just watch things decrease slowly over a given number of evaluations. So sometimes it decreases the length of the coils, but increases the coil-to-coil distance, and then it leads to a smaller quasi-symmetry, and all these things balance out so that the overall objective function, J, keeps decreasing over time. Therefore, in single-stage optimization, what we do is just sum these two objective functions together and have a very big array of degrees of freedom, which is the coil position and the boundary shape, and we change those at the same time. To have an optimizer find a solution efficiently, we find gradients of these objective function. And so we need to find gradients with respect to coils, gradients with respect to boundary. Some of these are analytical, some of these need finite differences. What we did is we benchmarked all of the analytic solutions that we found in order to have the most efficient method. But at the end of the day, there's always some finite differencing that takes place because with the code that we're using, which is called VMEC, which is called in Fortran, we don't have any auto-differentiation to find the derivatives in a better way. Therefore, a good way to make this optimization even more efficient is to use some sort of backpropagation or auto-differentiation through the MHD solver. But for now, we use finite differences for terms like quasi-symmetry and the MHD solution, and use everything that is coils an analytical derivative. And once we have an optimization, how do we assess if the optimization is doing well? Basically, we do Poincare plots. We just trace field lines from the coils, and if we see if they align perfectly with our MHD solution or not. So these are some of the results that we found. We start with a very constrained problem where we only have 4 coils. 2 of them are fixed. They're at the top and the bottom. And then 2 of them are interlinked. This is very similar to the CNT stellarator that operated at Columbia University. And it's very constrained because we have a very limited amount of coils. And what happens if we do first stage 1 independently from stage 2, we have very good quasi-symmetry. The stage 1 objective function is very low, but we're not able to find coils that reproduce that equilibrium, just because we only have a small amount of coils. And actually, we only have 1 independent coil because the other coil is just the mirror of the first coil. With single stage, we were able to find a much better solution with simpler coils, and the coils actually reproduce the target magnetic field. This is what Poincaré plot on the right. However, we had to give up on something, and the field is not perfectly quasi-symmetric just because we're constraining the problem that much. But at least we have a balance between the level of quasi-symmetry that we want and the level of coil complexity that we want. Another example is regular quasi-symmetry optimization. This is a quasi-symmetric stellarator with 3 field periods. It's a stellarator also with a reduced number of coils compared with typical number of coils, and we're able to find coils that have much lower B.N. And if we look carefully at the coils that are produced, they're also simpler than the other coils. All of this that I talked up to now was in vacuum. When we move to finite beta, there's a small caveat here. When we have a finite beta, so this means that we have a finite plasma pressure, we need to take that plasma magnetic field into account. So now we don't want to minimize B.N. We need to minimize only the target magnetic field .N. This is because the coils should only reproduce the vacuum magnetic field, and the plasma magnetic field should not come into account here. Therefore, we need to decouple the plasma from the coil magnetic field. And for this, we use a virtual casing principle that is able to give us the plasma magnetic field close to the plasma boundary. How to assess the optimization? Now, Poincaré plots don't work because if we just trace field lines around from the coils, these do not take the magnetic field from the plasma into account. Therefore, we need to run our MHD solver into free boundary mode so that it takes all of the plasma pressure into account, the beta into account, and do a comparison between the fixed and the free boundary solution. This is an example of a 4-coil stellarator again, but now with a 2% beta on axis, and we can see that now it has a Shafranov shift that is characteristic of these finite beta solutions. This is an example of a quasi-axisymmetric stellarator with finite beta. It has a 2.5% volume average beta, 5.3% beta on axis, and it's very constrained because it only has 4 coils. But we still are able to find a solution that closely reduces to the target magnetic field. However, as we've seen before, it kind of spoils a little bit the quasi-symmetry. So if we want to make a full design, we need to take this quasi-symmetry a little bit down and probably making the coils a little bit more complex. Now, there have been new developments in the algorithm. We've tried to find simplified stellarators using this algorithm that go outside the box and try to think a little bit differently than the ones that I presented before. When I mean simplified, I mean in terms of 3 different points of view. The first one is from an engineering perspective. We're trying to find coils that are simple to build, simple to maintain, things like planar coils or coils that do not link the plasma. Another one is from an operation perspective. We could try to find coils that have really large accessibility for ports and diagnostics, which is usually a problem for stellarators. And finally, from a design perspective, it would be good to have coils with a small number of degrees of freedom or small aspect ratios. And these 3 different points were addressed with different types of stellarators. So the first one that I'm showing here is a very simple stellarator, one of the simplest we could find. It's a stellarator with only 6 coils. This is very difficult to find with stage 1 plus stage 2 optimization, just because it's so constrained that we really need to have an optimization that tries to link the two and goes around hand by hand, trying to find a good boundary and a good set of coils. Here, these coils are circular, so they lead to circular flux surfaces. However, they don't have any sort of quasi-symmetry or quasi-isodynamic character to it. For this, we need to have a little bit more complex coils. In this example here, I show a stellarator with only 2 coils, and these 2 coils are interlinked together, and they're actually just rotations of the same coil. So in terms of design, this is very, very simple to create because I only have 1 coil with some degrees of freedom that creates a stellarator with actually a very big volume of really good flux surfaces. Another approach is to try to have coils that do not link the plasma. And I have such examples here. So on the left, I have a stellarator with coils that sit outside the plasma, and they have huge accessibility for the most part of the device. And we have 4 coils that link the plasma, 4 coils that are far away from the plasma. The caveat here is that the coils that are outside the plasma need to have a current that is 10 times larger than the ones that link the plasma, which may lead to huge forces. Therefore, for the future, if we want to invest on a design like this, we need to also do an optimization for reduced forces to see if we can have coils that are a little bit more realistic in that sense. On the right, I show a stellarator with coils that just sit outside the plasma, akin to trim coils, but not exactly. These just create an extra magnetic field here, but leave the inboard side of the stellarator without coils that can be used for other things. Another application is a stellarator that can have 2 different surfaces. This is the final application that I'm showing here. What this means is that I have coils that are changing currents, but their shape is the same. So in this animation, I have 7 different coils. And what I did is to have 2 different surfaces that are optimized at the same time. And these 2 surfaces can be different. However, whenever I have one set of currents, this should lead to one particular surface that is quasi-symmetric. And when I have another set of currents in the coils, they should lead to another surface that is also quasi-symmetric. And this way, I can have both a quasi-axisymmetric solution and a quasi-helical solution that can be operated in the same stellarator by just tuning the coil currents. Here on the right, I show magnetic field line traces from both coil currents, and you see how one stellarator is with respect to the other one. And on the bottom, I show the magnetic field strength on the plasma boundary, showing that it changes topology from a quasi-axisymmetric stellarator to a quasi-helical one. This is my last slide. As a conclusions, we have a single-stage optimization that is available on SimSoft that is able to find simple stellarators with quasi-symmetry. We have a finite beta case that is implemented and benchmarked using free boundary. And if you want to have more fun with single-stage configurations, the Flight Area Institute has a really nice database called Quasar that you can just go there and play around with all these visualizations. Okay, thank you very much.
Thank you very much, Rogerio, for this interesting talk. You showed a lot of interesting stellarator design and coils. So now we have time for questions. You can raise your hand or type in the chat. We have one, Jeff Candy. Given that you rely on VMEC that doesn't describe surface destruction, how do you address the problem of surface destruction and sensitivity to coil error? And and other potential causes of bad surfaces?
Yeah, so having a code that does not produce magnetic islands is actually a feature, not a bug. This is because if the code could accurately create chaotic fields and create a magnetic field that is very precise with magnetic islands, the optimization would be very, very noisy. This is because the things like quasi-symmetry and iota, a global iota, would be very hard to have a proxy for in these sort of chaotic fields. When we have a code like VMEC that gives a really nice set of nested flux surfaces for any boundary, although it doesn't reproduce the actual magnetic field that may be chaotic from the coils, it gives a very smooth approximation. Therefore, during the optimization, we take that smooth approximation into account. And as long as we converge to a solution that has very good surfaces and it's good enough, then whatever happens during the optimization is not as important.
Okay, thank you. We don't have more questions. I have a question myself. You showed some coils that are quite long, usually, in many of your plots. What's the reason for this? Because this is not practical for building these coils, and you need, these are expensive, I assume, and also you need a high current, a large current to circulate for these coils for a given magnetic field at the axis.
Yeah, that's right. The length of the coils is a parameter that comes into the optimization. And whenever we do an optimization in the objective function for stage 2, we have this L star. So L star is an input parameter for every coil optimization that we do. To create a realistic design, it would be better to have a scan over different L stars and see a sort of a Pareto front in what is the smallest L star that we can go that still has a good solution with good flux surfaces and good quasi-symmetry. In this work, we only used a single L star for everything. But yeah, I agree. We need to have smaller and smaller coil lengths until we're happy with our coil length and our quasi-symmetry.
Okay. And what about the two-in-one stellarator design with the same coils producing several configurations? I assume that you will have limitations in the configuration you can create with this. You can produce several ones, but with the same coils. But if you focus on the quality in some sense, maybe you are restricted. I don't know.
Yeah, it's actually very hard to find solutions like this because the problem is very constrained. A limitation that we see is that usually these sort of two-in-one stellators only work if one and the other can be inside a single vessel. So in this case, what we did, we started with a circular boundary, and we said that all of the stellators have to be inside this circular boundary. This is because the coils also have some sort of volume that they have to restrict the stellator inside. And so therefore, we cannot have stellators that are very far apart from each other or have very different topologies. So for example, it would be hard to have a QI and a QA just because one can go on the diagonal and the other is very circular. So it would be very hard to create something like that. For our case, what worked was to have a stellarator with the same number of field periods. So both of these solutions have 3 field periods. And we're able to find both a QA and a QH with 3 field periods. We couldn't find a QA with 2 field periods and a QH with 4 field periods, just because the topology was very, very different.
Yeah, I understand. But my question was also, what about the fidelity, the quality of the quasi-symmetry you produce? Is comparable to the case in which you only target one configuration?
In this case, no, in this case, it degraded a little bit, yeah. Just because we're constraining the problem even further, something has to give. So quasi-symmetry is the one that it's being degraded, yeah.
Okay, thank you very much.